Welcome back to Whispering Universes, where we journey to the most distant corners of our solar system and explore the worlds that challenge everything we thought we knew about planetary science. Tonight we turn our attention toward two giants that dwell in the outer darkness, so far from the sun that they exist in a twilight realm where sunlight arrives as barely more than the brightest star in Earth's sky. These are not the familiar giants of Jupiter and Saturn, with their enormous masses and prominent roles in our planetary family. These are different, stranger, smaller, colder, and in many ways more mysterious. These are Uranus and Neptune, the ice giants, and they're hiding secrets we're only just beginning to uncover. For most of human history, these worlds simply didn't exist in our awareness. While the 5 planets visible to the naked eye, Mercury, Venus, Mars, Jupiter, and Saturn, have been known since ancient times, woven into mythologies and tracked across the sky by countless civilizations, Uranus and Neptune remained hidden, too distant and too dim to reveal themselves without the aid of telescopes. Even after we developed the instruments to see them, they've remained somewhat neglected, overshadowed by their larger siblings, and relegated to the status of distant curiosities. Only one spacecraft, Voyager 2, has ever visited these worlds, and those were brief flybys in the 1980s, snapshots of planets we've had to study from afar ever since. But here's what makes these ice giants so fascinating, so worthy of our attention on this quiet night. They represent something fundamentally different in planetary architecture. They're not scaled-down versions of Jupiter and Saturn, not simply smaller gas giants. They occupy their own category, with interiors dominated not by hydrogen and helium, but by water, methane and ammonia, existing under such extreme pressure that they form exotic states of matter we can barely reproduce in laboratories. They possess magnetic fields that defy our understanding, tilted and offset in ways that shouldn't be possible according to standard planetary physics. Their atmospheres roar with winds that challenge the very laws of thermodynamics, moving faster than should be possible, given the minuscule amount of solar energy reaching these distant realms. And beyond their individual mysteries, Uranus and Neptune matter for a much larger reason. They're our only close-up examples of what appears to be the most common type of planet in the galaxy. When we survey exoplanets around other stars, we find that worlds roughly the size of these ice giants, planets larger than Earth but smaller than Jupiter, are extraordinarily abundant. Sub-Neptunes and mini-Neptunes orbit stars throughout the Milky Way, representing a planetary category that, ironically, doesn't even exist in the inner regions of our own solar system. Understanding Uranus and Neptune isn't just about comprehending two distant members of our planetary family. It's about developing a framework for understanding billions of worlds scattered across the cosmos. Tonight, we'll explore the complete story of these ice giants, from their discovery, through careful observation and mathematical prediction, to the exotic physics that governs their interiors, to the diverse systems of moons and rings that surround them, to the questions that still perplex planetary scientists decades after our only close encounter. We'll consider why Uranus lies on its side, knocked over in a way no other planet experiences. We'll examine how Neptune drives the fastest winds in the solar system despite receiving 900 times less sunlight than Earth. We'll visit Triton, the captured moon that erupts with nitrogen geysers despite surface temperatures of -235 degrees Celsius. And we'll contemplate Miranda, a moon that looks like it was shattered and reassembled, displaying geological features so extreme they challenge our understanding of what's possible on small, icy worlds. These are planets that demand patience from those who study them. They're so distant that sunlight takes hours to reach them, that radio signals from visiting spacecraft take hours to return to Earth, that their orbits around the Sun take the better part of a human lifetime. Uranus requires 84 years to complete one orbit. Neptune takes 165 years. This means that since Neptune was discovered in 1846, It has completed only one full circuit around the Sun, arriving back at the same position relative to the stars only in 2011. These are worlds that operate on timescales that exceed human experience, that reveal their secrets slowly, that require generations of scientists building on each other's work to gradually assemble a complete picture. As you settle into comfort tonight, preparing to drift towards sleep while we explore these distant realms, consider this. Right now, at this very moment, Uranus and Neptune are out there in the darkness, orbiting in their distant paths, their clouds roiling with weather patterns no human eye has witnessed in real time. Their moons silently circling in complex gravitational dances, their magnetic fields carving out magnetospheres in the thin solar wind that reaches their location. They continue their ancient journey around the Sun, whether we observe them or not, patient and persistent in the outer darkness, waiting for us to return and finally understand them properly. Here on Whispering Universes, we believe that every world in our solar system has a story worth telling, lessons worth learning, mysteries worth contemplating. The ice giants are no exception. In fact, they might be the most important planets we don't yet understand, holding keys to planetary formation, atmospheric dynamics, interior physics, and the nature of the most common worlds in the galaxy. So let's journey outward together, beyond the familiar territories of Mars and Jupiter, beyond the rings of Saturn, into the deep twilight at the edge of our planetary system, where two blue worlds spin in their unique ways, hiding secrets we're only just discovering. The story of discovering Uranus and Neptune is a story about extending human perception beyond its natural limits, about using technology and mathematics to reveal what remains invisible to unaided senses. It's a story that unfolds across decades, involving careful observation, theoretical prediction, international collaboration, and occasional bitter disputes over priority and recognition. These discoveries fundamentally changed our understanding of the solar system's scale and architecture, pushing the boundary of our cosmic neighborhood far beyond what ancient astronomers had imagined. On the night of March 13, 1781, William Herschel was conducting a systematic survey of the sky from his home in Bath, England, using a telescope he had constructed himself. Herschel was a musician by profession, a composer and oboist, but astronomy had become his passionate avocation, and he was methodically cataloguing every celestial object he could observe. On that particular night, while examining a region in the constellation Gemini, he noticed something unusual, a disk rather than a point of light, something that appeared different from the stars surrounding it. Initially, Herschel thought he had discovered a comet, which would have been notable but not revolutionary. But as he and other astronomers tracked this object over the following weeks and months, calculating its orbit, they realized something extraordinary. This was not a comet at all, but a planet, orbiting the Sun at nearly twice Saturn's distance. The discovery was accidental, in the sense that Herschel wasn't looking for a new planet. The very concept that additional planets might exist beyond those known, since antiquity wasn't part of contemporary astronomical thinking. But it was also the inevitable result of Herschel's systematic approach and improved telescope technology. Once humans developed the capability to see more clearly and survey more thoroughly, discovering Uranus became a matter of when, not if. Herschel initially wanted to name the planet Georgium Sidus, George's star, in honor of King George III, his patron. But the astronomical community eventually settled on Uranus, continuing the tradition of naming planets after figures from classical mythology. Uranus, the ancient Greek god of the sky and father of Saturn, seemed appropriate for a world beyond Saturn's orbit. The discovery of Uranus approximately doubled the known extent of the solar system overnight. If a planet could exist at that distance, what else might be out there? The question became more than philosophical in the early 1800s, as astronomers refined their calculations of Uranus's orbit and noticed something troubling. The planet wasn't quite where it should be. Even accounting for gravitational perturbations from Jupiter and Saturn, Uranus exhibited irregularities in its motion, arriving at predicted positions slightly early or late. These discrepancies were small but undeniable, and they suggested something was tugging on Uranus, something we couldn't see. This is where the story becomes a tale of mathematical triumph. In the 1840s, two mathematicians, working independently, John Couch Adams in England and Urbain Le Verrier in France, tackled the problem of explaining Uranus's orbital irregularities by hypothesizing that another, more distant planet was gravitationally perturbing its motion. Using Newton's law of gravitation and the careful observations of Uranus's position over decades, they calculated where this hypothetical planet should be. Their calculations represented an extraordinary achievement. Using only mathematics and the assumption that Newton's laws applied even at these extreme distances, they predicted the existence and location of a world no one had ever seen. Adams completed his calculations first in 1845, but struggled to get British astronomers to take his predictions seriously and search for the planet. Le Verrier, working independently, finished his calculations in 1846 and sent them to Johann Galle at the Berlin Observatory. On the night of September 23, 1846, Galle and his assistant, Heinrich Darest, pointed their telescope to the position Le Verrier had predicted, and within an hour they found Neptune, less than 1 degree from where Le Verrier said it would be. The discovery was announced immediately, and the planet was named Neptune, after the Roman god of the sea, perhaps because its blue colour suggested water, though that colour comes not from water, but from methane in its atmosphere. The discovery of Neptune stands as one of the great triumphs of theoretical astronomy. Here was a world found not by systematic searching or accidental observation, but by mathematical prediction, by following the logical implications of gravitational theory to their inevitable conclusion. It demonstrated that human understanding of physics had progressed to the point where we could predict the existence of invisible worlds and then find them exactly where calculations said they should be. It validated Newton's inverse square law at distances far beyond where it had been tested, and it confirmed that there were indeed more worlds in the outer solar system waiting to be discovered. But what exactly were Uranus and Neptune? Early observers could determine their sizes, masses, and orbits, but their nature remained unclear. They were obviously smaller than Jupiter and Saturn, with Uranus measuring about 4 times Earth's diameter and Neptune slightly smaller. Their masses were much less than the gas giants. Uranus is about 14.5 times Earth's mass, Neptune about 17 times, giving them much higher average densities than Jupiter or Saturn. This suggested a different composition, something heavier than hydrogen and helium. Early spectroscopy detected methane in their atmospheres, which was unusual, and gave both planets their distinctive blue-green colours. But understanding their true nature would require much more detailed observation, and eventually a visit by spacecraft. The term ice giant wasn't widely used until the late 20th century, after Voyager 2's flybys provided data that clarified these planets' internal structure. The name can be misleading. It doesn't mean these planets are giant balls of ice in the ordinary sense. Rather, it refers to the fact that their interiors are dominated by materials that astronomers call ices: water, methane, and ammonia, even though these materials exist at temperatures of thousands of degrees Kelvin and pressures of millions of atmospheres, forming exotic states of matter that bear little resemblance to the ice in your freezer. Understanding what ice giant really means requires diving deep into the chemistry and physics of planetary interiors, which is exactly where we're heading next. Among all the planets in our solar system, Uranus stands alone in its bizarre orientation. While other planets spin on axes that are more or less perpendicular to the plane of their orbits, Earth tilts at 23.5 degrees, Jupiter at just 3 degrees. Uranus lies on its side, with an axial tilt of 98 degrees. This means that Uranus essentially rolls around the Sun rather than spinning like a top, with its poles where other planets have their equators. For roughly 21 years at a time, one pole points almost directly at the Sun, while the other pole experiences continuous darkness. Then, as Uranus continues its 84-year orbit, the seasons gradually shift, with the Sun eventually appearing directly over the equator at the equinoxes, before the opposite pole becomes the one bathed in continuous sunlight. Imagine what this means for Uranian seasons. During the planet's solstices, one hemisphere experiences what amounts to a 42-year-long summer day, with the Sun spiraling around the sky but never setting, while the opposite hemisphere endures an equally long winter night. The Sun climbs higher and lower in these spirals, but if you were somehow standing at one of the poles during its summer, you would see the Sun circle around the horizon at a nearly constant altitude for decades. The amount of solar energy received by each hemisphere varies enormously over the course of Uranus's orbit, creating temperature differences and driving atmospheric circulation in ways we're only beginning to understand. Because Voyager 2 encountered Uranus near its solstice in 1986, the spacecraft essentially saw only one hemisphere properly illuminated, with the southern pole pointing almost directly at the Sun and the northern hemisphere largely in darkness. This extreme tilt raises an obvious question: how did Uranus end up this way? Planets form from rotating disks of gas and dust surrounding young stars, and they naturally acquire angular momentum in the direction perpendicular to the disk. All the planets should, therefore, have their rotational axes roughly aligned with the overall angular momentum vector of the solar system, which they mostly do. Jupiter, Saturn, Neptune, and even Earth all spin in orientations that make sense given solar system formation models. But Uranus breaks this pattern completely, suggesting that something dramatic happened in its history. The leading theory involves a giant impact, or possibly multiple impacts, early in Uranus's formation. Computer simulations suggest that a collision with an Earth-sized or larger object could have knocked Uranus onto its side, transferring enough angular momentum to dramatically alter the planet's spin axis. This isn't as unlikely as it might sound. The early solar system was a chaotic place, with planetary embryos migrating, colliding, and gravitationally scattering each other. We think Earth itself was struck by a Mars-sized object in a collision that created our Moon. Similar impacts probably occurred throughout the solar system during the final stages of planetary assembly, when large bodies were still common, but orbital configurations hadn't yet stabilized into the orderly arrangement we see today. But the impact hypothesis raises its own puzzles. If Uranus suffered a collision powerful enough to knock it onto its side, why do its major moons orbit almost exactly in the planet's equatorial plane, aligned with Uranus's tilted axis rather than with the solar system's original angular momentum? You'd expect the moons to remain in their original orbits, creating a system where the planet spins one way and the moons orbit in a completely different plane. Instead, the moons faithfully follow Uranus's equator. This suggests either that the impact happened very early, before the moons formed, allowing them to coalesce from a disk of debris that formed in the new equatorial plane, or that the moons somehow adjusted to the planet's new orientation through tidal interactions, though the latter scenario is difficult to explain physically. An alternative hypothesis suggests that Uranus's tilt might have evolved gradually through a resonance with Neptune during the early solar system's dynamical evolution. If Uranus and Neptune's orbits swept through particular configurations during planetary migration, resonant interactions could have slowly increased Uranus's tilt over millions of years without requiring a single catastrophic impact. This scenario has the advantage of potentially explaining both the tilt and the alignment of the moons, though it requires very specific orbital histories and remains controversial. The truth is, we don't yet know for certain how Uranus acquired its unusual orientation. It remains one of the enduring mysteries of planetary science, a puzzle left over from the solar system's violent youth. What we do know is that this tilt has profound effects on Uranus's atmosphere and climate. Despite receiving only about 1/400th the solar energy that Earth receives, and despite the extreme seasonal variations, Uranus shows surprisingly little temperature difference between its sunlit and dark hemispheres. When Voyager 2 arrived, finding the dark northern hemisphere almost as warm as the illuminated southern hemisphere, scientists were surprised. Heat is somehow being redistributed from the sunlit hemisphere to the dark one, presumably through atmospheric circulation, though the mechanisms remain unclear. Unlike Jupiter or Saturn, where the rapid rotation creates strong east-west winds organized into belts and zones, Uranus's slow rotation and extreme seasons create a more complex circulation pattern, one we've had difficulty observing and modeling. The tilt also affects Uranus's magnetosphere in interesting ways. As the planet rolls around the Sun, its magnetic field, which is itself tilted 59 degrees from the rotational axis and offset from the planet's center, points in wildly different directions relative to the solar wind during different parts of the orbit. This creates a magnetosphere that essentially tumbles as Uranus rotates, opening and closing different regions to solar wind bombardment every 17.2 hours as the planet spins. No other planet in the solar system experiences this kind of magnetospheric variation, and it creates conditions for auroras and charged particle interactions that we've barely begun to study. Recent observations using the Hubble Space Telescope and large ground-based telescopes with adaptive optics have revealed that Uranus's atmosphere is more dynamic than Voyager 2's images suggested. As the planet progressed from solstice toward equinox in the 2000s and 2010s, astronomers detected increasing storm activity, with bright clouds appearing at various latitudes. These storms tell us that Uranus's atmosphere responds to changing solar illumination patterns, that weather systems develop and evolve on this tilted world, and that the planet's apparent blandness during Voyager 2's visit might have been due to the unusual seasonal configuration rather than any inherent lack of atmospheric activity. Uranus, it turns out, is a dynamic world, one whose behavior we've only glimpsed during a single moment in its long year. As you contemplate Uranus rolling through space, one pole experiencing decades of sunlight while the other dwells in extended darkness, consider how this arrangement challenges our assumptions about what planets should look like. Here's a world that breaks the rules, that exists in a configuration that shouldn't persist yet clearly does, that operates according to its own logic, developed over billions of years in isolation at the solar system's edge. It reminds us that planets are individuals, not variations on a standard template, each with its own history, written in its physical properties and orbital characteristics. When Voyager 2 approached Neptune in August 1989, scientists expected to find a quiet, cold world, perhaps even more bland in appearance than Uranus had been 3 years earlier. After all, Neptune orbits 50% farther from the Sun than Uranus, receiving only about 40% as much solar energy. If solar heating drives atmospheric dynamics, then Neptune should be even less active than Uranus, its atmosphere sluggish and calm. What Voyager 2 actually found shocked everyone. Neptune possessed the fastest winds measured anywhere in the solar system, with features moving at speeds exceeding 2,000 kilometers per hour, more than twice the speed of sound in Earth's atmosphere. These winds howled in a place where they seemingly had no right to exist, powered by mechanisms that still puzzle planetary scientists today. The most striking feature Voyager 2 discovered was the Great Dark Spot, an anticyclonic storm system, roughly the size of Earth, churning in Neptune's southern hemisphere at about 22 degrees south latitude. Dark spots on Neptune, unlike the red or white spots on Jupiter, appear dark because they're regions where methane-rich atmosphere rises from deeper, warmer layers and then condenses out at higher altitudes, creating clearer regions where we see deeper into the darker atmospheric layers below. The Great Dark Spot rotated counterclockwise, as expected for a high-pressure system in the southern hemisphere, and the winds around it reached extraordinary speeds. Accompanying the Great Dark Spot were bright, white companion clouds, likely composed of methane ice crystals that formed when gas rising around the storm's periphery reached high enough altitudes to freeze. But here's the puzzle. Where does Neptune get the energy to drive such intense atmospheric dynamics? On Jupiter and Saturn, internal heat sources are obvious. Both planets emit roughly twice as much energy as they receive from the Sun, powered by slow gravitational contraction and, in Jupiter's case, helium rain in the deep interior. This internal heat drives convection, which combined with rapid rotation creates the banded structure and powerful jet streams we observe. Neptune also emits more energy than it receives from the Sun, about 2.6 times as much, but it's a much smaller planet with much less gravitational energy available. The amount of internal heat Neptune produces should be insufficient to drive winds faster than those on Jupiter, which receives nearly 900 times more solar energy and has a much stronger internal heat source. One possibility is that Neptune's heat is distributed more efficiently than in other giant planets, creating steeper temperature gradients that drive stronger convection and faster winds. The planet's smaller size might actually help here. Heat doesn't have to travel as far to reach the surface, potentially creating more vigorous circulation despite the lower total energy flux. Another factor might be the relative importance of different heat sources. On Neptune, internal heat dominates over solar heating much more than on Jupiter or Saturn, potentially creating a simpler, more efficient circulation pattern with fewer competing drivers and more direct conversion of thermal energy into kinetic energy. Recent studies have suggested that the winds might be concentrated in a relatively thin atmospheric layer, perhaps only a few hundred kilometers deep, rather than extending deep into the planet's interior. If the rapid winds are confined to this outer layer, they require less total energy to maintain, and small differences in temperature and pressure can drive them to high speeds without needing enormous energy inputs. This would make Neptune's atmosphere somewhat analogous to Earth's stratosphere, where relatively small temperature differences can drive powerful jet streams because the air is thin and friction is minimal. Neptune's atmospheric features prove surprisingly variable. The Great Dark Spot that Voyager 2 observed in 1989 had vanished by the time Hubble Space Telescope began regular observations of Neptune in 1994. In its place, a new dark spot appeared in the northern hemisphere, demonstrating that these features form, evolve and dissipate on timescales of years rather than persisting for centuries like Jupiter's Great Red Spot. Additional dark spots have appeared and disappeared in subsequent observations, suggesting that Neptune's atmosphere is in a state of continuous evolution, with storm systems arising from atmospheric instabilities, lasting for a period and then dispersing. The wind speeds themselves vary with latitude, creating a banded structure somewhat similar to Jupiter's, but less visually obvious because Neptune's cloud features are more subtle. The fastest winds blow westward at southern mid-latitudes, reaching those astonishing speeds of over 2,000 kilometers per hour. Near the equator, winds blow eastward at more modest speeds of a few hundred kilometers per hour. This creates strong wind shear between latitude bands, likely contributing to atmospheric turbulence and the formation of those impressive storm systems. The pattern suggests that Neptune, like Jupiter and Saturn, has organized its rotation and convection into a series of alternating east-west jets, though with its own unique characteristics, driven by its particular combination of size, rotation rate, and heat sources. The vertical structure of Neptune's atmosphere adds another layer of complexity. Like the other giant planets, Neptune has a troposphere, where temperature decreases with altitude, a stratosphere, where temperature increases with altitude due to methane-absorbing solar ultraviolet light, and a thermosphere, where temperatures rise even higher due to interactions with charged particles and solar wind. The transition between these layers creates complicated dynamics, with different wind patterns at different altitudes. Voyager 2 observations suggested that wind speeds might actually increase with altitude in some regions, which would be unusual and suggests interesting interactions between different atmospheric layers. Methane plays a special role in Neptune's atmosphere beyond just determining its colour. Methane can condense at Neptune's upper atmospheric temperatures, forming clouds and creating weather in the stratosphere, something that doesn't happen on Jupiter or Saturn, where methane stays gaseous. This means Neptune has active meteorology at multiple levels, with both convection from below, driving tropospheric weather, and methane condensation, creating stratospheric features. The interplay between these different types of weather systems adds complexity to Neptune's atmospheric dynamics and might contribute to the formation of those bright companion clouds we see accompanying dark spots. Understanding Neptune's winds matters beyond just explaining one planet's weather. Neptune likely represents a common type of world in the galaxy. Sub-Neptune and Neptune-sized exoplanets are abundant around other stars, many of them presumably ice giants with similar internal structures and atmospheric properties. If we can understand what powers Neptune's surprisingly vigorous atmosphere, we'll have better models for interpreting observations of these distant exoplanets, better predictions for what their weather and climate might be like. Neptune becomes not just an individual world, but a laboratory for understanding an entire class of planets scattered throughout the cosmos. As you drift towards sleep tonight, imagine those winds howling in Neptune's deep blue atmosphere, clouds racing across the planet at speeds that would rip apart any terrestrial structure, driven by heat flowing from deep within the planet, modulated by methane condensing in the thin, cold upper atmosphere. These winds have blown since before humans existed, will continue long after we're gone, patient and persistent in their violence, operating according to physical laws that govern fluid dynamics everywhere in the universe. To understand what ice giants really are, we need to journey inward, descending through their atmospheres into the high-pressure, high-temperature realms where ordinary chemistry gives way to exotic states of matter. The term ice giant refers not to their surface conditions. Both Uranus and Neptune have gaseous atmospheres, similar in some ways to Jupiter and Saturn, but to their interiors, where pressures reach millions of times Earth's atmospheric pressure, and temperatures soar to thousands of degrees Kelvin. Under these extreme conditions, materials that we think of as ices, water, methane, and ammonia, dominate the planetary structure, though they exist in forms so alien that calling them ice seems almost misleading. Let's start with the basic architecture. Both Uranus and Neptune consist of several distinct layers. At the very center lies a core, probably composed of rock and metal, silicates, iron, nickel, similar in composition to Earth's interior, but compressed to much higher densities. This core might contain anywhere from half an Earth mass to several Earth masses of material, though considerable uncertainty remains about its exact size and composition. Surrounding this rocky core is the ice mantle, a vast layer comprising perhaps 80 to 85% of the planet's mass. This mantle consists primarily of water, with substantial amounts of methane and ammonia mixed in, all compressed to extraordinary pressures and heated to temperatures of thousands of degrees. Finally, surrounding the ice mantle is a relatively thin atmosphere, perhaps 10 to 20% of the planetary radius, composed primarily of hydrogen and helium, with traces of methane and other compounds. The ice mantle is where things get interesting. At the pressures and temperatures that exist in this region, ranging from thousands to millions of atmospheres and thousands of degrees Kelvin, water doesn't exist as a solid ice, a liquid, or a gas in the ordinary sense. Instead, it forms what's called a supercritical fluid, a state of matter where the distinction between liquid and gas breaks down. Supercritical water is dense like a liquid, but flows like a gas, and its properties change continuously with depth as pressure and temperature increase. Mixed with methane and ammonia, this creates a complex chemical environment where different compounds interact, possibly separating into distinct layers or remaining mixed, depending on the exact conditions. Recent theoretical and experimental work has revealed even more exotic possibilities. At the extreme pressures deep in the ice mantle, water might form something called superionic ice. In this bizarre state of matter, the water molecules essentially break apart, with the oxygen atoms locked into a solid crystal lattice, while the hydrogen atoms move freely through this lattice like electrons in a metal. This makes superionic ice simultaneously solid and liquid. Solid in the oxygen framework, liquid in the hydrogen motion. It conducts electricity like a metal due to the mobile hydrogen ions, and it exists only at conditions so extreme we can barely reproduce them in laboratory experiments using diamond anvil cells or shock compression techniques. The presence of superionic ice in the interiors of Uranus and Neptune could explain some of their unusual properties, particularly their strange magnetic fields. If superionic ice exists deep in these planets and conducts electricity, it could host convective currents driven by internal heat flow. These currents, moving through a conducting material, would generate magnetic fields through dynamo action, similar to how Earth's liquid iron core generates our planet's magnetic field. The key difference is that superionic ice might exist in a relatively thin shell at a specific depth where pressure and temperature are just right, rather than filling a large volume like Earth's outer core. This could explain why Uranus and Neptune have magnetic fields that are tilted and offset from the planet's center. The dynamo operates in an asymmetric shell rather than a centrally located sphere. Another exotic phenomenon predicted to occur in ice giant interiors is diamond rain. Methane, which is abundant in these planets, consists of carbon and hydrogen atoms. At the extreme pressures and temperatures in the deep atmosphere and upper mantle, methane can break down, with the carbon atoms potentially forming diamond crystals that sink toward the planet's center while hydrogen rises. Laboratory experiments using high-powered lasers to shock compress mixtures mimicking ice giant conditions have actually observed diamond formation, suggesting this process might really occur. If it does, then deep beneath the visible surfaces of Uranus and Neptune, diamonds potentially as large as hailstones might be raining down through the superionic ice layers, slowly accumulating in a dense layer around the rocky core. The exact composition and structure of ice giant interiors remain uncertain because we can't observe them directly. Our understanding comes from combining several lines of evidence: the planet's masses and radii, which constrain their average densities, their gravitational fields, measured by spacecraft tracking, which reveal how mass is distributed, their thermal emission, which tells us about internal heat, and laboratory experiments and theoretical calculations about how materials behave under extreme conditions. Different models fit these constraints, leading to ongoing debates about details like the size of the core, the exact composition of the mantle, and whether distinct layers exist or materials remain mixed. One intriguing possibility is that Uranus and Neptune might differ in their internal structures despite their similar sizes and masses. Neptune emits significantly more internal heat than Uranus, about 2.6 times as much energy as it receives from the Sun, compared to Uranus's barely detectable internal heat. This difference could reflect different internal temperature profiles, different rates of cooling, or even different phase transitions occurring at different depths. Perhaps Uranus's interior has reached a state where convection is inhibited, preventing efficient heat transport from deep layers to the surface, while Neptune's interior remains more dynamically active. Or perhaps the giant impact that tilted Uranus also affected its internal structure, mixing core and mantle material in ways that altered the planet's thermal evolution. Understanding ice giant interiors matters for astrobiology, even though these planets themselves are unlikely to host life. The chemistry occurring in those deep, high-pressure layers, the interaction between water, methane, and ammonia, the formation of complex organic molecules, the possibility of liquid water layers at certain depths where pressure and temperature balance just right, might be relevant to other worlds. Some of the larger moons in the outer solar system, like Titan or Ganymede or Enceladus, might have high-pressure ice layers deep beneath their surfaces where similar chemistry occurs. And among the thousands of exoplanets we've discovered, many are ice giant-sized worlds orbiting other stars, perhaps with subsurface oceans or exotic interior chemistry that we're only beginning to imagine. As you relax into sleep tonight, imagine descending through Neptune's atmosphere, falling through ever denser gas until the distinction between atmosphere and interior blurs, pressure mounting until water transforms into a supercritical fluid, then deeper still until it crystallizes into superionic ice, oxygen atoms locked in place while hydrogen flows freely, strange convection patterns generating twisted magnetic fields, diamonds slowly raining down through this alien realm, settling toward a rocky core that has never seen sunlight, that will never see sunlight, existing in eternal darkness at temperatures of thousands of degrees. Before Voyager 2 encountered Uranus and Neptune, scientists had a reasonably good understanding of planetary magnetic fields based on observations of Earth, Jupiter, and Saturn. These planets' magnetic fields shared key characteristics. They were roughly dipolar, similar to a bar magnet, with field lines emerging from near one pole and entering near the other. They were approximately aligned with the planet's rotation axis, typically tilted by no more than 10 to 15 degrees, and they were centered on or very near the planet's center. This pattern made sense given our understanding of planetary dynamos, the processes by which electrically conducting fluids moving in a planet's interior generate magnetic fields. Rotating planets with liquid metallic cores or deep layers of conducting material should naturally produce magnetic fields aligned with their rotation axes. Uranus and Neptune shattered these expectations, revealing magnetic field geometries so strange that they forced planetary scientists to reconsider fundamental assumptions about how magnetic fields are generated. When Voyager 2 flew past Uranus in 1986, it discovered that the planet's magnetic field was tilted by 59 degrees from its rotation axis, far more than any other planet, and offset from the planet's center by about 30% of the planetary radius. This meant the magnetic field was neither aligned with Uranus's spin nor centered on the planet. Instead, it was askew, displaced, operating according to rules that didn't match our standard dynamo models. Scientists initially wondered if this strange configuration might be related to Uranus's unusual axial tilt. Perhaps the giant impact that knocked Uranus on its side also disrupted its interior in some way, creating an asymmetric magnetic field. Or perhaps Voyager 2 had caught Uranus during a magnetic field reversal, a period when the field's polarity flips, something that happens on Earth every few 100,000 years, and the field temporarily becomes disorganized. These explanations seemed plausible until Voyager 2 reached Neptune in 1989 and found almost exactly the same situation. Neptune's magnetic field was tilted 47 degrees from its rotation axis and offset from the planet's center by about 55% of the planetary radius. The odds of both ice giants being caught during field reversals were vanishingly small, and Neptune obviously hadn't suffered the same tilting impact as Uranus. Something else was going on. The key to understanding these bizarre magnetic fields lies in where they're generated. On Earth, the magnetic field comes from the liquid iron outer core, which occupies a substantial volume deep within the planet. Convection in this core, driven by cooling and compositional changes, combined with Earth's rotation, creates organized currents that generate a roughly dipolar field aligned with the rotation axis. On Jupiter, the field comes from liquid metallic hydrogen deep in the planet's interior, again producing an aligned dipolar field. But Uranus and Neptune don't have these deep, centrally located, conducting regions. Instead, as we discussed in the previous chapter, they likely generate their magnetic fields in a relatively thin shell of superionic ice, or electrically conducting fluid located at intermediate depths, perhaps about halfway from the center to the surface. If the dynamo operates in a shell rather than a deep core, the resulting magnetic field can be much more complex. Rather than producing a simple dipole, a shell dynamo can generate multiple magnetic poles, with field lines emerging and entering at various points rather than neatly organizing around two main poles. Computer simulations of shell dynamos show that they naturally produce fields that are tilted, offset, and multipolar, essentially matching what we observe at Uranus and Neptune. The field becomes a superposition of multiple magnetic components of different orders, dipole, quadrupole, octupole, and so on, creating the complex geometry that Voyager 2 measured. This unusual magnetic field structure has profound consequences for the planet's magnetospheres, the regions of space dominated by the planetary magnetic field rather than the solar wind. Earth's magnetosphere has a fairly consistent structure, a bow shock where the solar wind first encounters the magnetic field, a magnetopause boundary where planetary and solar fields balance, field lines stretched into a long magnetotail on the night side, and Van Allen radiation belts where charged particles are trapped. This structure rotates with Earth but maintains a fairly stable configuration relative to the Sun-Earth line. Uranus and Neptune's magnetospheres behave very differently. Because their magnetic fields are so tilted relative to their rotation axes, the magnetospheric structure essentially tumbles as the planet spins. The magnetic poles move in large circles relative to the planetary surface every 17.2 hours for Uranus and every 16.1 hours for Neptune. This creates a magnetosphere that repeatedly opens and closes different regions to solar wind, bombardment that stretches and compresses in complicated ways, that traps and releases charged particles in patterns unlike anything seen around other planets. Auroras on these planets would appear at unexpected latitudes, wandering across the planet as the magnetic field rotates, creating light shows that bear little resemblance to Earth's predictable auroral ovals or Jupiter's fixed auroral zones. The offset nature of the magnetic fields creates another interesting effect. The field strength varies dramatically across the planetary surface. At some locations, the magnetic field is strong. At others, it's quite weak. This means that moons orbiting close to the planet experience highly variable magnetic environments depending on where they are in their orbits. Triton, Neptune's largest moon, orbits through regions of strong and weak magnetic field, potentially affecting how solar wind particles interact with its thin atmosphere and how any sputtering or ionization processes operate on its surface. We still don't fully understand all the implications of these unusual magnetic fields. Questions remain about how exactly the shell dynamo operates, what drives the convection in the conducting layer, why the fields are tilted to such similar angles on both planets, despite their different rotation rates and thermal properties, and how the fields might vary over time. Unlike Earth's magnetic field, which we can monitor continuously, we have only snapshots of Uranus and Neptune's fields from Voyager 2's brief flybys. These fields might be evolving, drifting in orientation, strengthening or weakening in ways we can't detect from Earth. Understanding these fields matters for interpreting observations of exoplanets. As we develop the capability to detect magnetic fields around exoplanets through radio observations or their influence on stellar winds, we'll need models that include non-dipolar, tilted, offset fields like those of Uranus and Neptune. If ice giant-sized exoplanets commonly have similar field structures, that will affect how they interact with stellar radiation, how they retain their atmospheres, how they might protect any moons from charged particle bombardment. Uranus and Neptune are teaching us that magnetic fields come in more varieties than we once thought, that planetary interiors can generate fields in unexpected ways, and that we need to broaden our conceptual framework for understanding planetary magnetism. As you drift towards sleep, imagine the invisible magnetic fields surrounding Uranus and Neptune, twisted into complex geometries, rotating asymmetrically, field lines emerging at unexpected latitudes, carving out magnetospheres that tumble through space, deflecting solar wind particles, funneling them toward rotating auroral zones, creating electrical currents and particle accelerations in patterns no human has ever witnessed, patient and persistent in their strange dance. When you look at images of Uranus and Neptune, whether from Voyager 2, the Hubble Space Telescope, or ground-based observatories, the first thing you notice is their striking blue colour. Both planets appear as luminous blue orbs, distinctly different from the yellows and oranges of Jupiter and Saturn, or the browns and reds of Mars. This blue colour is not an artifact of photography or image processing, it's real, and it tells us something fundamental about these planets' atmospheric composition. But while we've long known the basic explanation for the colour, methane in their atmospheres absorbs red light, allowing blue to scatter back to space, recent observations have revealed that the complete story is more complex and that subtle differences between Uranus and Neptune's colours hint at important differences in their atmospheric structure. The basic mechanism for the blue colour involves methane, a simple molecule consisting of one carbon atom and 4 hydrogen atoms. Both ice giants have atmospheres composed primarily of hydrogen and helium, similar to Jupiter and Saturn, but with a higher proportion of heavier elements, including methane, water, and ammonia. In the upper atmospheres where sunlight penetrates, methane is the dominant coloured compound. Methane has a particular molecular structure that causes it to absorb light strongly in the red and infrared portions of the spectrum, while allowing blue and green light to pass through or scatter. When sunlight enters the atmosphere, the methane progressively absorbs the red wavelengths, so that light returning to space is depleted in red and enriched in blue. The deeper the light penetrates, the more red gets absorbed, and the bluer the reflected light becomes. This is similar to why Earth's oceans appear blue. Water absorbs red light more than blue light, so sunlight penetrating ocean water loses its red component and appears increasingly blue with depth. The difference is that on Earth, we're looking through liquid water over vertical distances of tens to hundreds of meters, while on Uranus and Neptune, we're looking through gaseous methane over vertical distances of many kilometers of atmospheric depth. The principle is the same. Selective absorption of red light leaves blue light dominant in what we observe. But here's the interesting detail. Neptune appears significantly bluer than Uranus, despite both having similar amounts of methane in their atmospheres. Spectroscopic measurements show that Uranus and Neptune have roughly the same methane abundance, about 2 to 3% by volume, in their upper atmospheres. If methane absorption were the only factor determining colour, they should appear almost identical. Instead, Neptune displays a deeper, more saturated blue, while Uranus has a slightly cyan or aquamarine tint, less vibrant and more pale. This difference persisted in all of Voyager 2's observations and continues in modern telescope images, indicating it's a real and persistent feature of these planets. For decades, this colour difference remained somewhat mysterious. Scientists proposed various explanations. Perhaps the atmospheres had different amounts of photochemical hazes. Perhaps cloud layers existed at different depths. Perhaps the scattering properties differed in ways related to atmospheric structure. Recent research using advanced spectroscopy and modelling has started to resolve the mystery, revealing that the colour difference likely involves a combination of factors, particularly the presence of different types of haze layers in the planet's upper stratospheres. A study published in 2022 used observations from the Gemini Observatory and Hubble Space Telescope to create detailed models of both planets' atmospheres, tracking how light of different wavelengths penetrates and scatters at various depths. The researchers found that both planets have a layer of haze particles in their stratospheres, likely formed from methane photochemistry, where ultraviolet sunlight breaks apart methane molecules and the fragments recombine into more complex hydrocarbons. But Uranus appears to have a thicker or more reflective haze layer than Neptune. This haze reflects some sunlight before it can penetrate deep enough for the methane to fully absorb the red wavelengths, effectively whitening Uranus's colour and making it appear less saturated. Neptune's thinner haze allows more light to penetrate deeper, where more complete red absorption occurs, resulting in the deeper blue we observe. The study also found differences in deeper cloud layers. Both planets have clouds of methane ice forming at altitudes where temperatures drop low enough for methane to condense. These clouds are not uniformly distributed, but rather occur in patches and layers, depending on local atmospheric conditions. Neptune appears to have more active cloud formation and perhaps thicker or more extensive methane ice clouds than Uranus, which might contribute to differences in how light scatters and reflects. The combination of haze properties and cloud distributions creates the subtle but distinct colour differences we observe. These findings raise interesting questions about why the atmospheric properties differ. Both planets have similar sizes, masses, and atmospheric compositions, so why would their haze and cloud characteristics be different? One possibility involves the planet's different internal heat emissions. As mentioned earlier, Neptune radiates significantly more internal heat than Uranus. This extra heat might drive more vigorous convection, creating stronger updrafts that affect how hazes and clouds form and are distributed vertically. The heat might also affect chemical reaction rates in the upper atmosphere, changing the properties of the photochemical hazes. Alternatively, the difference might be seasonal. Voyager 2 encountered Uranus near its solstice when one hemisphere had been in continuous sunlight for decades, potentially affecting atmospheric chemistry differently than at Neptune, which was observed at a different point in its seasonal cycle. Uranus's colour has been observed to change slightly over time as the planet has progressed from solstice toward equinox. Images from the 2000s and 2010s show Uranus appearing somewhat bluer and more active than in Voyager 2's 1986 images, with more visible cloud features and a slightly different overall hue. This suggests that the atmospheric properties, the haze thickness, the cloud distributions, perhaps even the methane abundance at different altitudes, vary with season as different parts of the planet receive different amounts of sunlight. If this is true, then Uranus and Neptune might not always show the colour difference we currently observe. Perhaps at different points in their long orbital periods, their appearances converge or diverge in different ways. Understanding these colour differences matters for studying exoplanets. As we develop the capability to directly image exoplanets and measure their colours and spectra, we'll need to interpret what we see in terms of atmospheric composition and structure. A planet's colour tells us about what molecules are present, what hazes and clouds exist, how light scatters and absorbs at different levels. The fact that Uranus and Neptune, despite their similarities, show measurably different colours due to subtle differences in haze and cloud properties reminds us how sensitive planetary appearance can be to atmospheric details. An exoplanet's colour might tell us not just what gases are in its atmosphere, but also about its vertical structure, its photochemistry, its dynamics, and perhaps even its internal heat flow. As you settle into sleep, imagine seeing Uranus and Neptune side by side, both glowing blue, but with subtle differences, one pale and cyan, the other deep and saturated, each colour encoding information about atmospheric structure, about methane and hydrogen and helium and tiny haze particles, about light penetrating and scattering and absorbing, transforming solar white light into these distinctive hues, a visual signature of these distant worlds' unique atmospheric conditions. Among all the moons in the solar system, Triton stands out as one of the most fascinating and unusual. It's the largest moon of Neptune, about 2,700 kilometers in diameter, making it the seventh largest moon in the solar system. Its surface temperature averages around -235 degrees Celsius, making it one of the coldest objects we've measured anywhere. Despite these frigid conditions, Triton is geologically active, with geysers erupting from its surface, spraying nitrogen gas and dark organic particles high into its thin atmosphere. And perhaps most remarkably, Triton orbits Neptune backwards. Its orbit is retrograde, meaning it moves opposite to Neptune's rotation, a clear sign that this moon didn't form where it currently resides, but was captured from somewhere else in the early solar system. When Voyager 2 flew past Triton in August 1989, making its closest approach to any object during its grand tour of the outer solar system, the spacecraft revealed a world unlike anything scientists expected. Triton's surface is remarkably young, with very few impact craters, suggesting that geological processes have resurfaced it within the last few 100 million years. The terrain displays a bizarre mixture of features, regions of cantaloupe-textured terrain, where the surface appears dimpled and ridged in complex patterns, smooth frozen plains likely covered by nitrogen ice, ridges and troughs indicating tectonic deformation, and dark streaks extending for hundreds of kilometers across the southern polar cap, evidence of those nitrogen geysers. The most dramatic discovery was detecting active geyser plumes erupting from Triton's surface in real time. Voyager 2's cameras captured images showing dark plumes rising kilometers above the surface and extending downwind for more than 100 kilometers before dispersing. These geysers work very differently from the water geysers on Earth or even the water ice geysers on Saturn's moon Enceladus. Triton's geysers are driven not by subsurface liquid, but by seasonal heating of surface nitrogen ice. During Triton's southern summer, which had been in progress for decades when Voyager 2 arrived, weak sunlight penetrates a meter or so into the translucent nitrogen ice covering the polar regions. This ice acts like a greenhouse, trapping solar heat beneath the surface. As temperature rises, the nitrogen ice turns directly into gas through sublimation. Pressure builds beneath the surface layer until it eventually breaks through, releasing a geyser of nitrogen gas that carries dark organic material up from beneath the ice. This discovery was remarkable for several reasons. First, it demonstrated that geological activity can occur on a moon at temperatures close to absolute zero, powered by nothing more than feeble sunlight. Second, it showed that you don't need liquid water or internal heat to have active geology. Solid nitrogen ice and sunlight suffice. Third, it revealed that complex organic chemistry occurs on Triton's surface, producing those dark compounds that streak across the polar ice. These organics likely form when methane and nitrogen in the atmosphere or ice are broken apart by ultraviolet sunlight and cosmic rays, then recombine into more complex molecules, a process called tholin formation, similar to what occurs on Saturn's moon Titan or on Pluto. But the most profound implication of Triton's geology relates to its origin and future. The retrograde orbit makes it nearly certain that Triton didn't form in orbit around Neptune. Instead, it was almost certainly a large Kuiper belt object, similar to Pluto or Eris, that wandered too close to Neptune sometime in the early solar system and was captured by the planet's gravity. The capture process would have been violent and disruptive. Triton's original orbit after capture would have been highly elliptical, carrying it close to Neptune and then far away in each orbit. Tidal forces during close approaches, the stretching and squeezing caused by Neptune's gravity acting differently on Triton's near and far sides, would have heated the Moon's interior, possibly melting much of it. Over millions of years, tidal interactions gradually circularized the orbit, dissipating the orbital energy as heat in Triton's interior and in Neptune's deep interior. This capture event had catastrophic consequences for Neptune's original moon system. Whatever moons existed before Triton's arrival would have been gravitationally disrupted, possibly knocked out of orbit entirely or shattered through collisions with Triton. The current population of smaller moons, including Proteus, Nereid, and several tiny irregular moons, likely formed after Triton's capture, either from debris of destroyed earlier moons or as fragments of the captured object itself. Nereid, with its highly eccentric orbit, might be a survivor from the pre-Triton era, its orbit perturbed into its current strange configuration by Triton's arrival and subsequent orbital evolution. Triton's capture and orbital evolution also explains why the Moon is geologically active today. The tidal heating that occurred during orbital circularization melted the interior and reset Triton's geological clock. Even now, although the orbit is nearly circular, tidal forces continue to generate some heat in Triton's interior. This heat, combined with radioactive decay of elements in Triton's rocky core, might maintain a subsurface ocean beneath the frozen surface. Some models suggest that Triton could have a layer of liquid water mixed with ammonia or other antifreeze compounds at depths of a few tens of kilometers beneath the surface. If such an ocean exists, it would make Triton potentially habitable, at least by the standards of microbial life, despite the extreme cold of its surface. But Triton's story has a tragic ending written in orbital mechanics. Because its retrograde orbit opposes Neptune's rotation, tidal forces are slowly robbing the Moon of orbital energy, causing it to spiral gradually inward toward Neptune. This is the opposite of what happens with our Moon, which is slowly receding from Earth because its orbit is prograde and Earth's tidal bulge pulls it forward. For Triton, Neptune's tidal bulge pulls it backward, stealing energy from its orbit. The process is slow. Triton loses only a few centimeters of orbital altitude per year, but inexorable. In somewhere between 10 million and 100 million years, Triton will reach what's called the Roche limit, the distance at which Neptune's tidal forces overcome Triton's own gravity. At that point, the Moon will be torn apart, its material spreading around Neptune to form a spectacular ring system, perhaps rivaling Saturn's rings in extent, though likely much less massive. This makes Triton a temporary moon, one that will exist for only a brief moment in geological time. The fact that we happen to exist during this brief window, when Triton is intact and orbiting Neptune, when we can observe its active geology and contemplate its captured origin, is a reminder of how fortunate we are to witness this particular configuration of the solar system. In a cosmic sense, we're seeing something transient, a stage in an evolution that will transform this captured Kuiper belt object into a beautiful ring system, which itself will eventually dissipate or be swept up by Neptune's atmosphere. As you drift towards sleep, imagine Triton in its lonely orbit, slowly spiraling inward toward Neptune, nitrogen geysers erupting from its frigid surface, organic compounds darkening its polar ice, a captured world far from its birthplace in the Kuiper belt, its doom sealed by the same orbital mechanics that captured it billions of years ago, yet patient in its journey, enduring for millions more years before its final transformation. If Triton is the most dramatic moon in the Neptune system, then Miranda holds that distinction for Uranus. Before Voyager 2's encounter with Uranus in January 1986, scientists expected Miranda to be a relatively boring world, a small icy moon only about 4,000 kilometers in diameter, probably heavily cratered and geologically dead like most small moons in the outer solar system. What Voyager 2's cameras revealed shocked everyone. Miranda displays some of the most extreme and varied geological features found anywhere, a surface that looks like it was assembled from mismatched pieces, a world that seems to violate the rule that small moons should be simple and inactive. The most striking features on Miranda are three large structures called coronae, roughly oval-shaped regions of parallel ridges and grooves that look completely different from the surrounding heavily cratered terrain. These coronae, named Arden, Inverness, and Elsinore, appear as if someone had carved or imprinted giant patterns onto the surface. Arden corona shows a pattern of parallel ridges and valleys, all running in roughly the same direction. Inverness corona displays a chevron or V-shaped pattern of ridges. These features are enormous relative to Miranda's size. Inverness corona alone is about 200 kilometers across, nearly half the moon's diameter. It's as if taking features the size of mountain ranges on Earth and fitting them onto a body not much larger than Colorado. Even more dramatic are the moon's vertiginous cliffs. The most famous is Verona Rupes, an enormous fault scarp, essentially a cliff, where one side of the surface has dropped relative to the other. Verona Rupes reaches a height of somewhere between 5 and 10 kilometers, making it the tallest known cliff face in the solar system. To put this in perspective, if you stood at the top of Verona Rupes and dropped a stone, it would fall for about 12 minutes before hitting the bottom, thanks to Miranda's low gravity. A human in a spacesuit stepping off the edge would take an hour. Similar amount of time to fall the entire distance, reaching a top speed of only about 200 kilometers per hour due to the low gravity. Enough to certainly be fatal, but much slower than would occur on Earth from a similar height. The ridged terrain, the coronae, the enormous scarps, all of these features demand explanation. How could such a small moon, which should have cooled and frozen solid billions of years ago, display evidence of such intense geological activity? Why do different regions look so different, as if they don't belong on the same world? Several theories have been proposed, each with its own challenges and supporting evidence. The most dramatic hypothesis, popular in the years immediately following Voyager 2's encounter, suggested that Miranda had been completely disrupted, blown apart by a catastrophic collision, and then reassembled from the pieces. In this scenario, the different terrain types represent different fragments of the original moon, now jumbled together after gravitational reassembly. The coronae might be pieces of the original interior, while the cratered terrain represents surface material. This theory has dramatic appeal and could explain the sharp boundaries between terrain types. However, computer simulations have shown that completely shattering and reassembling a body of Miranda's size is difficult. Most of the time, if a moon-sized object is hit hard enough to break apart, the pieces either escape entirely or form multiple smaller moons, rather than reassembling into one object. Moreover, if Miranda had been broken apart and reassembled, we'd expect to see evidence of impact melting and fracturing that we don't observe. A more current explanation involves tidal heating during periods of orbital resonance with other Uranian moons. Early in the system's history, Umbriel, Ariel, and Miranda might have been locked in orbital resonances, situations where their orbital periods were simple ratios, like 2:1 or 3:2. Such resonances enhance tidal forces, causing moons' orbits to become slightly elliptical. The varying distance from Uranus then creates cyclical tidal stresses that heat the interior through friction. If Miranda experienced sufficient tidal heating, it could have partially melted, with low-density ice rising and denser rocks sinking in a process called differentiation. The coronae might represent regions where this differentiation was most active, where partially molten ice rose in diapirs. Blobs of buoyant material pushing upward, creating the ridged patterns as the crust stretched and fractured above these rising plumes. This tidal heating scenario explains several of Miranda's features without requiring a catastrophic collision. The coronae would form through endogenous processes, forces from within, rather than representing reassembled fragments. The different terrain types would have formed at different times or in different thermal conditions, with corona forming during episodes of active, tidal heating and cratered plains representing quieter periods. The enormous cliffs might be normal faults that formed when the moon expanded slightly due to internal heating, or when it subsequently cooled and contracted, causing the surface to crack and portions to drop. A third possibility combines elements of both scenarios. Perhaps Miranda did experience a significant collision, not violent enough to completely shatter it, but energetic enough to heat the interior and trigger geological activity. The impact energy would have been converted to heat through friction and deformation, potentially melting parts of the interior. This heat would then drive convection and differentiation, creating the coronae. The collision might also have perturbed Miranda's orbit, leading to temporary resonances with other moons that sustained tidal heating for a period. In this view, both impact and tidal effects contributed to Miranda's bizarre geology. We may not be able to definitively resolve which explanation is correct, or whether some combination of all three factors played a role, without returning to the Uranus system with an orbital mission capable of detailed study. What's clear is that Miranda experienced geological activity far more intense than its size would suggest possible, and that this activity occurred recently enough in geological time that the evidence hasn't been erased by impacts or covered by debris. The fact that a moon barely large enough to pull itself into a sphere displays features rivaling those on much larger worlds tells us something important. Size alone doesn't determine geological potential. Location, timing, orbital interactions, and random collisions can conspire to create intense geology even on tiny bodies. Miranda also serves as a reminder of how much we miss by visiting worlds only briefly. Voyager 2 saw only about 40% of Miranda's surface, and that only at a resolution sufficient to see features larger than a few kilometers across. The other 60% remains completely unmapped at any meaningful resolution. We have no idea if similar coronae exist on Miranda's far side, or entirely different terrain types, or impact basins, or other surprises. Every world we've studied in detail has revealed unexpected features, and Miranda, which already shocked us with what little we've seen, undoubtedly has more secrets waiting in its unimaged hemisphere. As you close your eyes tonight, imagine Miranda tumbling in its orbit around Uranus, its broken surface half in sunlight and half in darkness. Those enormous cliffs casting shadows for hours as Uranus slowly rotates. The coronae traced with ridges and valleys, recording ancient episodes of geological violence. This small world carrying its scars from the solar system's chaotic youth, waiting patiently for humans to return and finally understand the forces that shaped it into one of the strangest moons ever discovered. Both Uranus and Neptune possess ring systems, though neither comes close to matching the magnificent rings of Saturn. These rings are dark, narrow, and incredibly faint, composed of particles that reflect very little light. They went undetected until the 1970s and 1980s, not because they're truly invisible, but because they're so different from Saturn's bright, reflective ice rings that astronomers weren't looking for such dim features. The discovery and study of these ring systems has revealed fascinating dynamics, particularly the crucial role played by small shepherd moons that gravitationally confine ring particles and prevent them from spreading out and dissipating. Uranus's rings were discovered first, in 1907, through a technique called stellar occultation, watching a star pass behind the planet and monitoring how the starlight dims. Astronomers expected the star to gradually disappear as Uranus's atmosphere passed in front of it, remain hidden while the planet blocked the star, then gradually reappear on the other side. Instead, they observed brief, unexpected dips in the star's brightness before and after the main occultation, symmetrical on both sides of the planet. These dips indicated that something was orbiting Uranus, repeatedly blocking the starlight as the planet moved across the star. That something turned out to be a system of narrow rings, each only a few kilometers wide, but thousands of kilometers in circumference. Voyager 2's encounter in 1986 confirmed these rings and discovered additional fainter ones, bringing the total to 13 main rings. The most prominent, called the Epsilon ring, is about 20 to 100 kilometers wide and remarkably narrow considering its radius of about 51,000 kilometers from Uranus's center. The rings are incredibly dark. They reflect only about 2% of incident light, making them among the darkest objects in the solar system. They're probably composed of rock fragments and organic material rather than the relatively pure water ice that makes up Saturn's rings. This dark material might be radiation-processed methane or more complex carbon compounds, gradually darkened over millions of years by ultraviolet light and charged particles. The narrowness of Uranus's rings presents a puzzle. Orbital mechanics predicts that ring particles should gradually spread out over time through collisions and gravitational perturbations. A narrow ring should broaden, dissipating into a more diffuse structure. Yet Uranus's Epsilon ring maintains its narrow width. The solution involves shepherd moons, small moons orbiting just inside and outside the ring. Voyager 2 discovered two such moons flanking the Epsilon ring, named Cordelia and Ophelia. These tiny satellites, each only about 20 to 40 kilometers in diameter, gravitationally shepherd the ring particles, preventing them from spreading. Cordelia, orbiting inside the ring, accelerates particles that drift inward, pushing them back outward. Ophelia, orbiting outside the ring, decelerates particles that drift outward, causing them to fall back inward. Together they create a gravitational channel that confines the ring particles. Neptune's rings were discovered later and proved even more mysterious. Ground-based stellar occultations in the 1980s produced confusing results. Sometimes they detected ring-like features, sometimes they didn't, and the features didn't appear symmetrically on both sides of the planet. This led to speculation about ring arcs, incomplete rings that extended only partway around the planet rather than forming continuous circles. Such structures seem to violate basic orbital mechanics. Particles in Keplerian orbits should spread around the entire orbit over time. There's no reason they should remain clumped in arcs. Voyager 2's arrival at Neptune in 1989 confirmed that the ring arcs were real, but it also revealed something crucial. Neptune has complete rings, and the arcs are just regions where the rings are much denser, containing more material than the surrounding portions. There are 5 main rings, named for astronomers who contributed to Neptune's discovery and study: Gale, Leverrier, Lassell, Arago, and Adams. The Adams ring, outermost at about 63,000 kilometers from Neptune's center, contains the prominent arcs, which have been given colorful names: Liberté, Égalité, Fraternité, after the French Revolution's motto, and Courage. The persistence of these arcs, despite orbital mechanics' tendency to smear them out, requires an explanation. The answer again involves a shepherd moon, though in a more complex way than at Uranus. A small moon called Galatea orbits just inside the Adams ring, and it's locked in a 42-43 orbital resonance with the material in the ring arcs. This means that for every 42 orbits Galatea completes, particles in the arcs complete 43 orbits. This specific resonance creates regions where gravitational perturbations from Galatea prevent particles from spreading out, essentially trapping them in the arc regions. It's similar to how Jupiter's gravity traps asteroids in stable regions called Lagrange points, but operating in a different resonance configuration. However, observations over the decades since Voyager 2's encounter have shown that Neptune's ring arcs are not actually stable. Images from the Hubble Space Telescope and large ground-based telescopes using adaptive optics have revealed that the arcs have changed significantly since 1989. Some arcs have faded or shifted position, new features have appeared. The Liberté arc has dimmed dramatically and might have dissipated entirely. This suggests that Neptune's ring arcs are temporary features that form, evolve and dissipate on timescales of decades to centuries. They might represent debris from impacts on nearby small moons, temporarily concentrated by Galatea's gravitational influence before gradually spreading out or falling into Neptune's atmosphere. Both ring systems raise questions about longevity. Rings are inherently temporary structures. The particles within them collide, gradually grinding each other down into smaller fragments. Atmospheric drag affects the innermost ring particles, causing them to spiral inward. Radiation and charged particles sputter atoms from particle surfaces. Over millions of years, ring systems should erode and dissipate unless they're replenished with new material. Saturn's massive rings might be relatively young, perhaps only a few 100 million years old, formed from a disrupted moon or large comet. Uranus and Neptune's much less massive rings are probably even younger or actively replenished by meteoroid impacts on nearby moons or by material ejected from those moons through cryovolcanism or impact gardening. The shepherd moons themselves also raise interesting questions. These tiny satellites are so small that we know almost nothing about them beyond their approximate sizes and orbits. How did they form? Are they captured objects, fragments from larger moons, shattered by impacts, or rubble piles that accreted from ring material? Their surfaces and compositions remain mysteries. Some of them might be temporary, destined to be disrupted by tidal forces or impacts over geological time, which would affect the ring structures they currently shepherd. Understanding ring dynamics around Uranus and Neptune helps us interpret observations of ring systems around other planets and even around some asteroids, where recently discovered narrow rings defy expectations and probably require shepherd satellites we can't yet detect. Every ring system is different, operating according to the same physical laws, but producing diverse outcomes depending on the planet's gravity, rotation rate, satellite system, and history. The subtle rings of the ice giants, so different from Saturn's spectacular displays, remind us that even when phenomena share basic characteristics, the details matter enormously, and each system tells its own story. As you relax into sleep, imagine those dark, narrow rings orbiting in the cold darkness around Uranus and Neptune, barely visible, barely holding together against the forces that want to pull them apart, shepherded by tiny moons that patrol their boundaries, particles colliding in slow motion, abrading each other, creating microscopic dust, some of it falling toward the planet, some escaping. The rings slowly evolving over timescales far longer than human civilization, patient in their delicate dance. Beyond Miranda, the Uranian system includes 4 larger moons, discovered by William Herschel and his son John in the late 1700s and early 1800s. These are the classical moons, Ariel, Umbriel, Titania, and Oberon, named after characters from Shakespeare's A Midsummer Night's Dream and Alexander Pope's The Rape of the Lock. They range from about 1,160 kilometers in diameter, Ariel, to 1,580 kilometers, Titania, making them substantial worlds in their own right, though smaller than Earth's moon or the Galilean satellites of Jupiter. Voyager 2's brief flyby in 1986 provided our only close-up views of these moons, revealing diverse geology, that hints at complex histories involving both tidal heating and impact events. Titania, the largest of Uranus's moons, displays a surface dominated by impact craters, but also shows clear evidence of past geological activity. Enormous fault canyons scar its surface, some more than 1,000 kilometers long, evidence that Titania underwent global-scale tectonic deformation. These canyons appear to be normal faults, regions where the crust pulled apart with one section dropping down relative to the adjacent terrain. This suggests that Titania's interior once expanded, perhaps due to the transition of high-pressure ice to a less dense form as the interior cooled, or possibly due to water in the interior freezing and expanding. The surface also shows signs of resurfacing, with some regions having fewer craters than others, indicating that geological processes erased older craters in those areas. Some models suggest that Titania might have experienced differentiation early in its history, with rocky material sinking toward the center and ice rising to form a mantle, possibly with a layer of liquid water between the rock core and ice shell. If this ocean existed, tidal heating from orbital resonances with other moons might have kept it liquid for an extended period. However, at Titania's current orbital distance, and with its nearly circular orbit, tidal heating should be minimal. Any subsurface ocean would have frozen long ago unless some unusual heating mechanism persists, perhaps residual heat from radioactive decay in the rocky core. Current models suggest Titania is probably frozen solid now, but its surface tells a story of a more active past. Oberon, the outermost large moon, is slightly smaller than Titania and appears older based on its heavily cratered surface. Unlike Titania, Oberon shows little evidence of large-scale tectonic features. Its most distinctive characteristic is the presence of several large impact craters with very bright rays emanating from them, stretching for hundreds of kilometers across the surface. These rays consist of bright, relatively fresh ice excavated by the impacts and deposited on the surrounding darker terrain. Some of Oberon's craters have dark material on their floors, possibly cryovolcanic material, water mixed with ammonia and methane that welled up from the interior after the impacts, taking advantage of the fractures created by the impact to reach the surface. One particularly intriguing feature on Oberon is a mountain on its limb, the edge of the visible disk, that rises about 6 kilometers above the surrounding terrain. This mountain was visible in Voyager 2's images as a prominent peak silhouetted against space. Its origin remains uncertain. It might be central peak material from a large impact basin just beyond the visible limb, or a tectonic uplift feature, or perhaps ejecta from a major impact elsewhere on the moon. Without more complete coverage and better resolution images, we can only speculate about its true nature. Ariel, despite being the fourth largest moon, shows the most extensive evidence of past geological activity among the classical Uranian moons. Its surface is crisscrossed by enormous valleys and fault scarps, some of which have broad, smooth floors that appear to have been resurfaced by some process, possibly cryovolcanic flows or perhaps tectonic smoothing. These valleys cut through older cratered terrain, clearly indicating they formed relatively recently in geological terms. Some regions show very few impact craters, suggesting surface ages of perhaps only a few 100 million years, quite young compared to the solar system's 4.5 billion year age. The extensive tectonic activity on Ariel demands explanation. The moon is relatively small, only about 1,160 kilometers in diameter, and should have cooled and frozen solid long ago. Yet its surface clearly experienced significant deformation and possible cryovolcanism. The most likely explanation involves tidal heating during past orbital resonances. If Ariel was once locked in resonance with Miranda and Umbriel, the resulting tidal heating could have partially melted its interior, allowing geological activity to continue for extended periods, even on this small world. When the resonance eventually broke, perhaps due to tidal evolution or perturbations from other moons, the tidal heating would have ceased and Ariel would have begun freezing from the core outward, creating the extensional faults we observe as the interior contracted during cooling. Umbriel presents a stark contrast to Ariel. Despite being similar in size, about 1,170 kilometers in diameter, Umbriel appears dark and heavily cratered, with few signs of past geological activity. Its surface is the darkest among Uranus's large moons, reflecting only about 16% of incident light compared to 40% for Ariel. This dark material is probably carbonaceous compounds or radiation-processed methane, similar to what we find on many outer solar system objects. Umbriel's most distinctive feature is a bright ring on the floor of the crater Wunda, near the moon's equator. This bright ring appears to be relatively fresh ice exposed by the impact, though its ring-like distribution within the crater, rather than forming a central peak or covering the entire floor, is puzzling. The contrast between Umbriel and Ariel raises intriguing questions. Why would two similarly sized moons in the same system have such different geological histories? One possibility is that Ariel participated in tidal heating episodes that Umbriel avoided, perhaps because the orbital resonances involved Ariel and Miranda but not Umbriel. Another possibility involves differences in composition. Perhaps Umbriel has more rock and less ice, making it more rigid and less susceptible to tidal deformation. Or perhaps Umbriel experienced fewer large impacts in its history, which on other moons might have fractured the crust and allowed cryovolcanic material to reach the surface. Without more detailed observations and data on these moons' masses, compositions, and internal structures, we can only hypothesize about the causes of their differences. All four classical moons raise the tantalizing possibility of subsurface oceans. Even though current models suggest these moons are frozen solid, during earlier periods when tidal heating was more intense, or before radiogenic heat sources had decayed, liquid water layers might have existed between the rocky cores and icy mantles. These oceans would have been mixed with ammonia and other compounds that act as antifreeze, lowering the freezing point and potentially allowing the liquid to persist longer. If such oceans existed, they would have represented potentially habitable environments, at least for simple organisms, with water, organic compounds, and energy from tidal heating, three essential ingredients for life as we know it. The fact that we've only seen each of these moons once, in brief flybys that captured at best half their surfaces at moderate resolution, means we know very little compared to what could be learned from orbital missions. We don't know the moon's masses precisely enough to determine their densities and internal structures. We have only vague spectroscopic data on their surface compositions. We don't know if any of them currently have subsurface oceans or volcanic activity. Each of these worlds deserves dedicated study, not just flybys, but orbiters capable of radar sounding, gravity measurements, detailed spectroscopy, and comprehensive imaging. Until we return to Uranus with that kind of mission, these moons will remain tantalizing mysteries, worlds we've glimpsed but barely begun to understand. Beyond the regular moons, those large spherical satellites orbiting in the equatorial planes of Uranus and Neptune, lie populations of irregular moons, small objects in distant, inclined and often eccentric orbits. These irregular satellites are almost certainly captured objects, asteroids or Kuiper belt objects that strayed too close to the ice giants and were gravitationally trapped in the early solar system. Studying these moons tells us about the populations of small bodies that once populated the outer solar system, about the mechanisms of gravitational capture, and about the violent collisions that have shattered some of these captured objects into families of fragments. Uranus has 9 known irregular moons discovered so far, while Neptune has 7. These numbers are much lower than at Jupiter or Saturn, which have dozens of irregular satellites. The difference probably reflects observational difficulty more than any real absence. these moons are extremely small, typically only a few kilometers to a few tens of kilometers in diameter, orbiting at distances of millions of kilometers from their planets. They're incredibly faint, visible only in long exposure images from large telescopes, and they move slowly across the sky, requiring multiple observations over months or years to confirm their orbits. Many more likely exist, waiting to be discovered, as survey telescopes become more sensitive and dedicated searches continue. The irregular moons fall into families based on their orbital characteristics. At Uranus, there's a prograde family with orbits tilted about 30 to 40 degrees from the planet's equator, and a retrograde family with orbits inclined more than 140 degrees, essentially orbiting backwards relative to Uranus's rotation. The members of each family have similar orbital inclinations and distances, suggesting they might be fragments from collisions that broke apart larger captured objects. If you shatter a moon through an impact, the fragments will initially have very similar orbits to each other, differing only slightly due to the velocities imparted by the impact. Over time, gravitational perturbations and the small velocity differences cause the fragments' orbits to diverge, but they retain a family resemblance in their orbital parameters. Neptune's irregular moons show a similar pattern. The prograde family includes several small moons in somewhat eccentric orbits inclined about 30 to 50 degrees from Neptune's equator. But the most interesting is Nereid, which doesn't fit the pattern of the other irregular moons. Nereid is much larger, about 340 kilometers in diameter, and follows an extremely eccentric orbit that carries it from about 1.4 million kilometers to 9.7 million kilometers from Neptune over its 360-day orbital period. This is the most eccentric orbit of any large moon in the solar system. Such an orbit is difficult to explain through simple capture. Instead, Nereid might be a survivor from Neptune's original regular satellite system, its orbit perturbed into its current extreme configuration when Triton was captured. The gravitational chaos of Triton's capture would have disrupted the orbits of any pre-existing moons, potentially ejecting some entirely, shattering others through collisions, and throwing survivors like Nereid into highly perturbed orbits. The composition and physical properties of these irregular moons remain largely mysterious. They're too small and distant for detailed spectroscopy or imaging, so we know little about what they're made of. By analogy with captured moons at Jupiter and Saturn, and with asteroids and Kuiper Belt objects more generally, we expect they're composed of mixtures of rock and ice, probably with higher rock fractions than the regular moons. Their surfaces are likely covered with dark organic material, possibly similar to the material seen on Trojan asteroids or outer main belt asteroids. Some might be more ice-rich, resembling short-period comets or Kuiper Belt objects. Others might be predominantly rocky, similar to C-type or D-type asteroids. One way to learn more about these objects is through careful observation of their light curves, how their brightness varies as they rotate. These variations, caused by the moons presenting different faces toward us as they spin, can tell us about their shapes and rotation periods. Observations have found that many irregular moons have rotation periods of just a few hours, which is consistent with them being small rubble piles held together loosely by gravity. A few show more complex light curves, suggesting irregular shapes or possibly binary systems. Two objects orbiting each other while both orbit the planet. Such binaries would provide direct measurements of the object's masses through their mutual orbital dynamics, giving us crucial density information. The irregular moon populations also tell us about the conditions in the early solar system when these objects were captured. Gravitational capture of objects on unbound hyperbolic trajectories is difficult under normal circumstances. For a passing object to become gravitationally bound, it needs to lose energy somehow. Otherwise, it just swings past and continues on its way. Several mechanisms might accomplish this. The object could break apart during close approach, with one fragment gaining energy, escaping, while the other loses energy, becoming captured. The object could interact with a pre-existing disk of gas or debris around the planet, losing energy through drag. Or the capture could occur during a period when the planet's orbit was migrating, creating what's called pull-down capture, where objects that were initially in solar orbits, similar to the planet's orbit, get left behind as the planet migrates away, effectively capturing them. The nice model of solar system evolution, which describes how the giant planets migrated from their formation locations to their current orbits, provides context for understanding irregular moon capture. During the migration period, when Jupiter moved inward and the other giant planets moved outward, the planets would have encountered vast numbers of small bodies in the primordial planetesimal disk. Gravitational interactions would have scattered many of these bodies throughout the solar system, and some would have been captured as irregular satellites. The timing of this migration, thought to have occurred several hundred million years after the planets formed, fits with the evidence from irregular moon families, which show signs of subsequent collisional disruption after capture, requiring time for impacts to have occurred after the captures. Studying these distant faint moons might seem like an esoteric pursuit with little practical importance, but they serve as time capsules from the solar system's youth. Their compositions preserve information about the materials present in the outer solar system before planet migration scrambled everything. Their orbital distributions constrain models of planet migration and satellite capture. The collision families tell us about impact, rates and conditions in the early outer solar system. Each of these small moons is a piece of the puzzle, and together they help us reconstruct the dynamic history of our planetary system's formation and evolution. As you settle deeper into sleep, imagine these tiny moons in their vast, lonely orbits, taking months or even years to circle Uranus or Neptune. Their surface is ancient and dark, fragments of larger objects shattered long ago, captured from the space between planets during the solar system's youth, now trapped in endless repetition, silently bearing witness to the violence and chaos that shaped the worlds we see today. Every piece of close-up data we have about Uranus and Neptune came from a single spacecraft during brief encounters in 1986 and 1989. Voyager 2's journey to these distant worlds represents one of humanity's greatest exploratory achievements, a mission that took advantage of a rare planetary alignment occurring only once every 175 years, executed with technology from the 1970s that's now hopelessly obsolete, but somehow still functions billions of kilometers from Earth. Understanding what Voyager 2 accomplished and what it couldn't accomplish during its brief visits helps us appreciate both how much we've learned and how much remains unknown about the ice giants. Voyager 2 launched from Cape Canaveral on August 20th, 1907, 16 days before its twin, Voyager 1. Both spacecraft were designed to take advantage of a fortunate planetary alignment that would allow a single spacecraft to visit multiple outer planets using gravity assists, essentially borrowing orbital energy from one planet to reach the next. Voyager 1's trajectory was optimized for close encounters with Jupiter and Saturn, particularly Saturn's moon Titan, which meant sacrificing the ability to continue to Uranus and Neptune. Voyager 2's trajectory was designed to keep the option open for extending the mission to the ice giants if the spacecraft remained healthy after Saturn. After successful encounters with Jupiter in July 1979 and Saturn in August 1981, revealing incredible details about those systems, Voyager 2 was approved for the extended mission to Uranus and Neptune. The challenges were immense. The spacecraft would be traveling farther from the Sun than any previous mission, to regions where sunlight is so weak that solar panels become useless. Voyager used radioisotope thermoelectric generators, RTGs, powered by plutonium-238 decay for electricity. The spacecraft would be so distant that radio signals, traveling at light speed, would take hours to reach Earth, making real-time control impossible. The instruments and cameras, designed in the early 1970s, would be operating in much dimmer conditions than intended, requiring long exposures and careful image motion compensation to avoid blurring. Voyager 2 reached Uranus on January 24, 1986, making its closest approach at about 81,500 kilometers from the planet's cloud tops. The encounter was brief. Most science data was collected over a period of a few days around closest approach, but incredibly productive. Voyager discovered 10 new moons, confirmed the existence of Uranus's rings, and measured their properties in detail, measured the planet's magnetic field, and discovered its bizarre offset and tilted configuration. Took the only close-up images we have of Miranda, Ariel, Umbriel, Titania, and Oberon, measured atmospheric composition and temperature profiles, and collected data on the magnetosphere and particle environment. However, the encounter had significant limitations. Voyager approached Uranus during the planet's southern summer solstice, when the southern pole pointed almost directly at the Sun. This meant that much of the northern hemisphere was in darkness and couldn't be imaged. The spacecraft's trajectory, determined by the need to reach Neptune later, constrained which moons could be approached closely and from what angles. Only Miranda received truly close-up imaging. The other large moons were viewed from greater distances, revealing less surface detail. The brief duration of the encounter meant that atmospheric dynamics and magnetospheric processes could only be sampled at one moment in time, providing no information about variability or evolution. After Uranus, Voyager 2 continued outward on a 3.5-year journey to Neptune. The spacecraft team used the intervening time to refine techniques for operating in low-light conditions, to develop new software for image processing and data compression, and to plan an encounter that would maximize science return during the brief close approach. They particularly wanted close encounters with Neptune's large moon Triton, whose retrograde orbit and potential geological activity made it a high-priority target, and with the planet itself to measure its atmospheric dynamics and internal magnetic field. Voyager 2 reached Neptune on August 25, 1989, passing about 4,950 kilometers above the North Pole, the closest approach to any planet during the entire Grand Tour. The encounter revealed Neptune to be far more dynamic than Uranus, with powerful winds, large storm systems, including the Great Dark Spot, and active weather patterns. The spacecraft discovered 6 new moons and confirmed the existence of Neptune's rings with their unusual arc structures. It measured Neptune's magnetic field and found it to be similar to Uranus's in its extreme tilt and offset. Most dramatically, the Triton flyby revealed active nitrogen geysers erupting from the moon's surface, a completely unexpected discovery that revolutionized thinking about geological activity in the outer solar system. The Triton encounter was especially challenging because it required Voyager to pass very close to the moon, only about 40,000 kilometers, to obtain the desired image resolution and scientific measurements. This close approach occurred after the Neptune flyby, meaning the spacecraft's trajectory at Neptune had to be designed to enable the Triton encounter as well. The dual goals constrained the mission design, but resulted in extraordinary science from both the planet and its most interesting moon. After Neptune, Voyager 2 continued on a trajectory, taking it out of the solar system at an angle to the ecliptic plane. Unlike Voyager 1, which headed upward relative to the plane of the planets after passing Saturn, Voyager 2 headed downward. Both spacecraft are now in interstellar space, having crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium. Voyager 1 in 2012 and Voyager 2 in 2018. They continue to transmit data about conditions in this unexplored region, though their RTG power output declines by about 4 watts per year, and instruments are being shut down one by one to conserve power. Both spacecraft will probably fall silent sometime in the 2030s as power becomes insufficient to operate any instruments or transmit signals to Earth. The legacy of Voyager 2's encounters with Uranus and Neptune cannot be overstated. Everything we know about these planets' atmospheres, interiors, magnetic fields, rings and moons comes from those brief flybys, supplemented by Earth-based observations that lack the resolution and comprehensive measurements that only a spacecraft can provide. Every image of Miranda's fractured terrain, every measurement of Neptune's winds, every data point about Triton's geysers came from Voyager 2's instruments during those few hours of closest approach. No subsequent mission has visited either planet, and none is currently en route, meaning that for my entire lifetime, and perhaps yours, Voyager 2's data represents the totality of our close-up knowledge of the ice giant systems. This makes us acutely aware of how much we don't know. We've seen only portions of most moon surfaces. We've sampled atmospheric and magnetospheric conditions at only one moment in each planet's long year. We have no data on seasonal variations, no long-term monitoring of weather patterns, no detailed gravity measurements to determine internal structures, no comprehensive spectroscopy to map compositional variations. Voyager 2 answered many questions, but raised even more, leaving us hungry for a return mission that could study these systems properly, that could orbit rather than fly by, that could monitor variations over extended periods, that could apply modern instruments and techniques to these fascinating worlds. As your thoughts drift towards sleep, imagine Voyager 2 racing outward through the darkness between stars, now more than 20 billion kilometers from Earth. Its cameras long since shut down to conserve power, its plutonium heart slowly cooling, its last messages transmitted to the enormous radio dishes that strain to hear its faint whisper across the void, carrying with it the story of the ice giants, humanity's messenger to these distant worlds and beyond. Among the many puzzles presented by the ice giants, one of the most perplexing concerns Uranus's internal heat, or more precisely, its apparent lack thereof. All of the giant planets in our solar system emit more energy than they receive from the Sun, powered by slow gravitational contraction and internal heat left over from their formation. Jupiter radiates about 1.7 times as much energy as it absorbs from sunlight. Saturn emits roughly 1.8 times its absorbed solar energy. Neptune, despite being smaller and much farther from the Sun, emits about 2.6 times as much energy as it receives. These internal heat sources drive convection in the planet's interiors, power atmospheric dynamics, and represent the slow cooling of these worlds over billions of years. But Uranus breaks the pattern. It emits essentially no detectable internal heat, with measurements showing an internal heat flux barely distinguishable from zero, certainly no more than 10% above the absorbed solar energy, and possibly zero. This absence is puzzling for several reasons. Uranus should still retain substantial heat from its formation 4.5 billion years ago. Planetary formation is a violent process involving countless high-velocity collisions that convert kinetic energy into heat. The final assembly of a planet involves accretion of thousands or millions of planetary embryos, each impact depositing enormous thermal energy. This heat doesn't disappear quickly. It takes billions of years for a planet-sized body to radiate away all its primordial heat into space. Neptune, which is similar in size and mass to Uranus, clearly hasn't finished cooling. Why would Uranus be different? Moreover, Uranus should be generating additional heat through gravitational contraction. As a planet cools, it contracts very slowly, perhaps only a millimeter or so per year, but even this tiny contraction converts gravitational potential energy into heat. For Jupiter and Saturn, this slow contraction, combined with differentiation processes like helium rain in Jupiter's deep interior, provides significant ongoing heat generation. Uranus should experience similar processes, yet the heat apparently isn't reaching the surface, or perhaps isn't being generated in the expected amounts. Several hypotheses attempt to explain Uranus's missing heat. The most dramatic suggests that the giant impact believed to have knocked Uranus on its side might have also fundamentally altered the planet's thermal structure. If the impact was energetic enough and occurred late in Uranus's formation, it could have stripped away part of the planet's primordial atmosphere and mixed core and mantle material in unusual ways. This mixing might have created a composition gradient in the interior, a gradual change in the ratio of rock to ice from the core to the surface rather than distinct layers. Such a gradient could inhibit convection, preventing heat from the deep interior from efficiently reaching the surface. In a convecting planet, hot material rises and cool material sinks, efficiently transporting heat from the interior to the surface where it can radiate into space. But if composition varies with depth, convection can be suppressed. The technical term is doubly diffusive convection, where two factors affect whether material rises or sinks: temperature and composition. Hot material wants to rise, but if it's compositionally heavier than the overlying layers, gravity pulls it back down. The result can be a stable stratification, where heat transport occurs primarily through slow conduction rather than efficient convection. If Uranus's interior is stratified in this way, heat would take much longer to reach the surface, creating a situation where the deep interior remains warm but little heat emerges. An alternative explanation focuses on the phase diagram of water and other ices at high pressure. At the extreme conditions in Uranus's interior, different forms of ice can exist at different depths depending on temperature and pressure. Some of these phase transitions, changes between different crystalline structures, can affect the planet's thermal evolution. If a particular phase transition creates a layer of increased viscosity or altered thermal conductivity, it might impede heat flow from deeper regions. Recent laboratory experiments have explored the properties of water and water-ammonia mixtures at the pressures and temperatures relevant to ice giant interiors, finding complex behavior that could potentially affect thermal transport. A third possibility is that Uranus actually does have internal heat, but we simply haven't detected it accurately. The measurements of Uranus's thermal emission come primarily from infrared observations that detect radiation escaping from the planet's upper atmosphere. If clouds, hazes, or atmospheric opacity affects how efficiently internal heat reaches the altitudes we observe, we might underestimate the true internal heat flux. Neptune's deeper blue color and clearer atmosphere might allow internal heat to escape more efficiently, making its internal heat more readily detectable. Uranus's thicker hazes and different atmospheric structure might trap internal heat at depths we can't observe with infrared telescopes. A more exotic hypothesis suggests that Uranus's interior underwent a major disruption or reorganization relatively recently in geological time, say within the last billion years. This reorganization could have involved a massive convective overturn, where material from different depths suddenly exchanged positions. Such an event would release a burst of thermal energy that the planet is still radiating away, temporarily suppressing the need for ongoing internal heat generation to reach equilibrium. However, explaining what would trigger such an overturn in a planet that had been stable for billions of years is challenging. The different internal heat emissions of Uranus and Neptune might also relate to subtle differences in their interior compositions or structures. Perhaps Neptune has a higher concentration of heavy elements that slowly sink toward the center, releasing gravitational energy as they fall. Or perhaps Neptune has more radioactive elements in its rocky core, generating heat through ongoing decay. Models of ice giant formation suggest that both planets captured different amounts of solid material during formation, depending on their exact locations and the local density of the protoplanetary disk. These compositional differences, though probably small, might have significant effects on long-term thermal evolution. Understanding Uranus's thermal evolution is more than an academic curiosity. It has practical implications for understanding the planet's dynamics and structure. Internal heat drives atmospheric convection and weather. The lack of apparent internal heat might explain why Uranus appeared so bland during Voyager 2's encounter compared to Neptune's dynamic atmosphere. If Uranus's atmosphere is driven almost entirely by weak solar heating rather than by vigorous convection, from below it would naturally be less active. However, recent observations showing increased storm activity on Uranus as it progressed toward equinox suggest that the planet is more dynamic than Voyager 2 saw, complicating this simple picture. The mystery also affects our interpretation of exoplanet observations. As we develop techniques to measure the thermal emission of ice giant-sized exoplanets, we'll need models that account for the possibility that some of these worlds might have suppressed heat transport, like Uranus. This would affect their atmospheric temperature profiles, their weather patterns, their evolution over time, and their appearances in both reflected light and thermal emission. If Uranus-like thermal properties are common among ice giants, that fundamentally changes our predictions for what we'll observe as exoplanet characterization improves. Resolving the mystery of Uranus's missing heat requires a dedicated orbital mission with instruments capable of precise measurements of the planet's thermal emission at multiple wavelengths and locations. By mapping how temperature varies with latitude, altitude, and time, and by measuring the planet's gravitational field precisely enough to constrain interior structure models, we could distinguish between the various hypotheses. Does Uranus truly lack internal heat, or are we simply not measuring it correctly? Is the interior stratified, suppressing convection, or is heat being generated but trapped at depth? Only by returning to Uranus with modern instruments can we hope to answer these questions definitively. As you drift deeper into sleep, imagine the interior of Uranus. Vast layers of exotic ices under crushing pressure, super hot, yet somehow not releasing their heat to the surface, whether trapped by compositional barriers or suppressed convection or some process we haven't yet imagined. That heat remaining locked away in the darkness, waiting patiently for billions more years or until some future reorganization releases it, the planet keeping its thermal secrets close. Our solar system contains only 2 ice giants, but the universe contains billions upon billions. When astronomers began discovering planets around other stars in the 1990s and 2000s, they initially found mostly hot Jupiters, gas giant planets orbiting extremely close to their stars, completing orbits in days rather than years. These were easiest to detect with early techniques because they're massive and tug strongly on their stars, and because they pass in front of their stars frequently, blocking starlight and revealing themselves through transit observations. But as detection methods improved and surveys expanded, a different picture emerged. The most common type of planet in the galaxy is not a hot Jupiter, not an Earth-like world, but something in between. Planets with radii between Earths and Neptunes, with masses ranging from a few Earth masses to about 20 Earth masses. These sub-Neptunes and mini-Neptunes dominate the exoplanet population, and Uranus and Neptune are our only local examples for understanding what these worlds might be like. The terminology can be confusing. Astronomers typically call planets with radii between Earths and about 1.7 Earth radii super-Earths, suggesting rocky worlds larger than our own. Planets with radii between 1.7 and 4 Earth radii, roughly Neptune's size, are called mini-Neptunes or sub-Neptunes, suggesting they have substantial atmospheres and possibly icy interiors. The boundary between these categories is somewhat arbitrary and probably doesn't represent a sharp transition in nature, but it reflects A key insight: planets in this size range can't be simply scaled-up versions of Earth. Above about 1.5 to 2 Earth radii, planets likely have thick hydrogen-helium atmospheres or substantial water ice mantles, making them fundamentally different from terrestrial planets. Surveys from the Kepler Space Telescope and other exoplanet hunting missions have found these Neptune-sized worlds around a significant fraction of all stars, orbiting at various distances from close-in hot Neptunes to more distant cold Neptunes. Their ubiquity is puzzling given that our solar system doesn't have any such planets in the inner regions. Between Earth at 1 Earth radius and Saturn at 9.4 Earth radii, we have nothing, a gap that would be filled with sub-Neptunes if our system were typical. This missing planet in our solar system, the lack of anything between 1 and 4 Earth radii, is one of the puzzles that drives comparative planetology. Did our solar system somehow fail to form such planets? Or did we form them and then lose them, perhaps scattered away during the giant planet migration, described by the NICE model? Understanding sub-Neptune exoplanets requires understanding ice giants like Uranus and Neptune, because we can study the ice giants in detail, while exoplanets remain mostly characterized by just their masses, radii, and orbital parameters. By modeling Uranus and Neptune's interiors, atmospheres, and thermal evolution, we develop frameworks that can be applied to interpreting exoplanet observations. When we measure an exoplanet's mass and radius, we can calculate its average density and compare it to models based on different compositions, rocky like Earth, icy like Uranus, or gas-rich with a thick hydrogen atmosphere. The resulting constraints tell us what the planet is probably made of, even though we can't see its interior directly. One key insight from studying Uranus and Neptune is that ice giant is a misleading term for most sub-Neptune exoplanets, which orbit much closer to their stars than Uranus and Neptune do to the Sun. At those close distances, the surface temperature can be hundreds or even thousands of degrees Kelvin. The ices, water, methane, ammonia, wouldn't be icy at all, but would exist as supercritical fluids or even plasmas. Yet the compositional framework developed for ice giants still applies. These are planets whose interiors are dominated by materials heavier than hydrogen and helium but lighter than rock, with substantial atmospheres of hydrogen and helium surrounding these cores. They're thermally inflated compared to cold ice giants, but the basic structure, rocky core, ice-water mantle, hydrogen-helium atmosphere, remains relevant. Recent observations using the James Webb Space Telescope and large ground-based telescopes have begun characterizing sub-Neptune atmospheres through transmission spectroscopy. When these planets pass in front of their stars, starlight filters through their atmospheres, and different molecules absorb light at different wavelengths. By comparing the star's spectrum with and without the planet in front, we can detect the atmospheric composition. These observations have found evidence for water vapor, methane, carbon dioxide, and other molecules in sub-Neptune atmospheres, confirming that they're chemically similar to ice giants, though much hotter. One surprising discovery from exoplanet surveys is the radius valley, or Fulton Gap, a relative scarcity of planets with radii around 1.5 to 2 Earth radii. Below this gap are super-Earths, mostly rocky. Above it are mini-Neptunes with substantial atmospheres. The gap might represent a divide between planets that retained their primordial hydrogen-helium atmospheres and those that lost them through photoevaporation, the process where intense radiation from the nearby star heats the upper atmosphere to escape velocity, allowing it to stream away into space. Small planets close to their stars would lose their atmospheres entirely, leaving behind bare rocky cores, while larger planets have enough gravity to retain substantial atmospheres despite photoevaporation. The exact location and properties of this radius valley constrain models of atmospheric escape and planet formation, connecting back to fundamental questions about how planets acquire and retain their atmospheres. Studying exoplanet demographics, the statistical properties of planet populations rather than individual worlds, reveals patterns that tell us about planet formation and migration. Sub-Neptunes are most common around stars of about 1 solar mass, less common around more massive or less massive stars. They show a preference for certain orbital periods, creating pile-ups in the period distribution that might reflect migration pathways or resonant trapping. Some stars have multiple sub-Neptunes in compact systems, where several planets orbit closer than Mercury does to our Sun. These configurations require formation mechanisms very different from what produced our solar system's architecture, perhaps involving formation farther out, followed by extensive inward migration, or in situ formation in unusually massive protoplanetary disks. The diversity of sub-Neptune exoplanets also teaches us that Uranus and Neptune represent just 2 points in a vast parameter space. Some sub-Neptunes are water worlds with deep global oceans beneath hydrogen atmospheres. Others might be predominantly rocky with relatively thin atmospheres. Still others could have exotic interiors we haven't imagined, with carbon-rich compositions creating layers of diamond or graphite, or sulfur-rich compositions creating entirely different chemical environments. The conditions in these planets, temperatures, pressures, compositions, create states of matter we can barely explore in laboratories, requiring us to extrapolate theory into regimes where experiments provide few constraints. One particularly intriguing class of sub-Neptune exoplanets are the mini-Neptunes in the habitable zone, planets orbiting at distances where surface temperatures would allow liquid water if not for their thick hydrogen atmospheres. These planets probably aren't habitable on their surfaces because those thick atmospheres create enormous greenhouse effects, raising temperatures to hundreds of degrees. But some models suggest they could have habitable conditions at certain altitudes in their atmospheres, where temperature and pressure balance just right, or potentially on large moons orbiting these planets, if such moons exist. Understanding whether ice giant-sized planets can host life, either in their atmospheres or on their moons, depends crucially on understanding their atmospheric chemistry, dynamics, and evolution, areas where Uranus and Neptune provide our only detailed case studies. The James Webb Space Telescope and upcoming missions like the European Space Agency's Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, are specifically designed to characterize exoplanet atmospheres, with particular emphasis on sub-Neptunes and mini-Neptunes. These observations will reveal the chemical compositions, cloud properties, and temperature structures of ice giant analogues around other stars, providing the comparative context that makes Uranus and Neptune's properties more meaningful. Are their atmospheric compositions typical or unusual? Are their magnetic field configurations common among ice giants or unique to our solar system? Do most ice giants emit internal heat like Neptune or suppress it like Uranus? Only by studying many examples can we understand what's universal and what's specific to individual planetary histories. Understanding ice giants also matters for the emerging field of astrobiology beyond traditional habitable zones. While we typically think of habitable worlds as rocky planets in the narrow orbital range where surface water remains liquid, some astrobiologists have begun considering whether life could emerge in the atmospheres of ice giants or their large moons. Uranus and Neptune themselves seem unlikely to host life. Their atmospheres are too turbulent, with strong vertical motions that would carry any hypothetical organisms into destructive high-temperature regions deep in the atmosphere. But Triton demonstrates that ice giant moons can be geologically active and potentially habitable in subsurface oceans. If sub-Neptune exoplanets commonly have large moons, as the giant planets in our solar system do, those moons might represent habitable environments even around planets that are themselves inhospitable. The study of exoplanets also feeds back into our understanding of solar system formation. The existence of hot Jupiters and close-in sub-Neptunes demonstrates that planet migration is common, supporting models like the NICE model that invoke extensive migration to explain our solar system's current architecture. The diversity of exoplanetary systems shows us that there's no single path to planetary system formation. Different initial conditions and random events produce radically different outcomes. Our solar system, with its particular arrangement of small rocky planets, inner, giant gas planets in the middle, and ice giants in the outer regions, is just one possibility among many. Understanding why we have the system we do requires understanding what other systems are possible and what processes lead to different architectures. As telescope technology continues advancing, we're approaching the capability to directly image ice giant exoplanets rather than just detecting them indirectly through their gravitational effects or transits. Direct imaging would allow us to measure their colors, detect clouds and storms, monitor seasonal changes, and perhaps even detect auroras or other manifestations of magnetic fields. These observations would transform ice giant science from the study of two examples to a field with dozens or eventually hundreds of comparison cases, each with its own mass, orbital distance, atmospheric properties, and evolutionary history. Uranus and Neptune would become reference points in a vast catalogue rather than isolated curiosities. The ultimate goal is to understand not just individual planets, but the principles that govern planetary formation, composition, structure, and evolution across all possible masses and orbital configurations. Ice giants occupy a crucial middle ground in this understanding, more massive than terrestrial planets, but less massive than gas giants, close enough to study in detail, but representative of the most common planetary type in the galaxy. Every measurement we make of Uranus and Neptune, every model we develop to explain their properties, every mission we send to explore them contributes to this larger framework that will eventually allow us to understand planets everywhere, to predict what we'll find around any given star, and perhaps to identify which worlds might harbour life. As your thoughts drift towards sleep, imagine the countless ice giants scattered across the galaxy, orbiting red dwarf stars and sun-like stars and massive blue stars. Some hot and swollen, others cold and compact, some with rings and moons and active weather, others perhaps quiet and featureless, each one a variation on themes we first encountered at Uranus and Neptune, each one telling its own story of formation and evolution. Billions of distant worlds we'll never visit, but can understand through studying our own ice giants. The orbits of Uranus and Neptune today, nearly circular, reasonably well separated, tilted only slightly from the solar system's general plane, create an impression of order and stability. But this orderly arrangement is almost certainly not where these planets formed, nor has it existed unchanged since the solar system's birth. Instead, growing evidence suggests that the giant planets underwent dramatic orbital migration in the solar system's first billion years, moving inward or outward by substantial distances, gravitationally scattering each other and countless smaller bodies, fundamentally reshaping the solar system's architecture. Understanding this migration is crucial for understanding how Uranus and Neptune acquired their current properties and why the outer solar system looks the way it does today. The story begins with planet formation theory. Planets form in protoplanetary disks, rotating disks of gas and dust surrounding young stars. In the inner regions where temperatures are high, only rocky and metallic materials condense from the gas, forming terrestrial planets. Beyond what's called the ice line, the distance from the star where temperatures drop low enough for water to freeze, ices become available as solid building material, dramatically increasing the amount of material that can accumulate into planets. This is why the giant planets formed in the outer solar system rather than the inner regions. They needed the additional mass provided by ices to grow large enough to capture substantial hydrogen and helium atmospheres. But here's a puzzle. Forming ice giants at Uranus and Neptune's current distances presents significant challenges. At those distances, the protoplanetary disk was probably quite sparse, with relatively little mass per unit area. This means the timescale for accumulating planetary cores through collisions would have been very long, perhaps tens of millions of years or more. Yet the gas disk, from which these planets needed to capture their hydrogen-helium atmospheres, probably dissipated after only a few million years, blown away by the young sun's energetic radiation and stellar wind. How could Uranus and Neptune have grown fast enough to capture atmospheres before the gas disappeared? One solution is that Uranus and Neptune didn't form at their current distances, but rather much closer in, perhaps in the region between Jupiter and Saturn. At those distances, the disk would have been denser, allowing faster core growth. Once the cores reached sufficient mass, perhaps 10 to 15 Earth masses, they could begin capturing gas from the surrounding disk. But they probably formed late enough or grew slowly enough that they captured relatively little gas compared to Jupiter and Saturn, which explains why they're ice giants with modest hydrogen-helium envelopes rather than gas giants dominated by hydrogen and helium. After formation, gravitational interactions with remaining planetesimals, the swarm of smaller bodies filling the protoplanetary disk, began pushing the planets around. When a planet gravitationally scatters a planetesimal, sending it into a different orbit, conservation of momentum requires that the planet's orbit also change slightly in the opposite direction. Individually, these changes are tiny, but over millions of encounters with countless planetesimals, they add up. Generally, planets tend to migrate in directions determined by the distribution of planetesimals around them and by gravitational interactions with other planets. The NICE model, named after the city in France where much of this work was developed, provides a specific scenario for how this migration occurred in our solar system. In the NICE model, Jupiter, Saturn, Uranus, and Neptune initially orbited in a more compact configuration than today, with spacings that might have placed Uranus and Neptune considerably closer to the Sun than their current positions. A massive disk of planetesimals, perhaps 30 to 50 Earth masses worth, extended beyond the planets. As the planets slowly migrated due to interactions with this disk, with the outer planets generally migrating outward and Jupiter migrating slightly inward, they eventually reached a configuration where Jupiter and Saturn entered a 2-1 orbital resonance, Jupiter completing exactly 2 orbits for every 1 orbit of Saturn. This resonance was dynamically unstable and triggered a period of chaotic evolution. The planets' orbits became more eccentric and tilted. They crossed each other's paths, experiencing close encounters that radically altered their orbits. Uranus and Neptune were scattered outward, potentially even switching positions. Some versions of the NICE model suggest Neptune formed inside Uranus's orbit and was scattered outward past it. The planets plunged through the planetesimal disk, scattering most of its mass either into the Sun, out of the solar system entirely, or into distant orbits, forming what we now know as the Kuiper Belt and Oort cloud. This period of chaos, sometimes called the Late Heavy Bombardment, also sent a shower of asteroids and comets into the inner solar system, creating the spike in impact cratering visible on the Moon and other inner solar system bodies. The NICE model explains several otherwise puzzling features of the solar system. It explains why Neptune orbits farther from the Sun than Uranus despite being more massive. It was scattered to a more distant orbit during the migration chaos. It explains the structure of the Kuiper Belt, with its various dynamical populations and orbital resonances with Neptune, as the natural outcome of Neptune scattering planetesimals as it migrated outward. It explains the existence of Jupiter's Trojan asteroids, objects sharing Jupiter's orbit but leading or trailing it by 60 degrees, has captured planetesimals during the migration period. It even potentially explains why Mars is so small compared to Earth and Venus. Perhaps Jupiter's inward migration prevented Mars from accreting more material. For Uranus and Neptune specifically, the migration model explains how they could have formed relatively quickly in denser regions of the protoplanetary disk and then been moved to their current distant locations. It also provides a mechanism for Triton's capture. If Neptune was migrating outward and encountering a population of large Kuiper belt objects, one of those objects could have been captured if the encounter occurred at just the right velocity and geometry, or if Neptune had a temporary atmosphere of gas and dust that provided drag to capture the object. However, the NICE model is not without challenges and uncertainties. The timing of the migration remains debated. Did it occur 500 million years after solar system formation, as suggested by lunar crater chronology, or earlier or later? The exact initial configuration of the giant planets is uncertain, with different studies proposing different starting arrangements. Some versions of the model include a fifth giant planet that was ejected from the solar system entirely during the chaotic phase, though evidence for this remains indirect. And alternative models propose different migration scenarios or question whether such dramatic migration occurred at all, suggesting instead that the planets formed close to their current positions and that the late heavy bombardment had different causes. Testing these models requires multiple lines of evidence. Crater chronology on inner solar system bodies constrains when the impact spike occurred. The orbits and compositions of Kuiper belt objects reveal how Neptune's migration affected the outer solar system. The orbits of asteroids, particularly Trojans, and irregular satellites of the giant planets, provide information about capture mechanisms during migration. The interior compositions of the giant planets, if we can determine them precisely, would tell us about conditions where they formed. Each piece of evidence helps refine or reject specific migration scenarios. Understanding planetary migration also connects to exoplanet science. Hot Jupiters, gas giants orbiting extremely close to their stars, almost certainly formed farther out and migrated inward, either through gravitational interactions with the protoplanetary disk or through gravitational interactions with other planets. The compact multi-planet systems we observe, with several sub-Neptunes orbiting within Mercury's orbit, probably involved extensive migration. Migration appears to be the rule rather than the exception in planetary system evolution, making our understanding of how it occurred in our own solar system directly applicable to interpreting exoplanet observations. As you drift deeper into sleep tonight, imagine the early solar system in chaos, Jupiter and Saturn entering resonance and destabilizing everything, Uranus and Neptune scattered like billiard balls across the outer solar system, planetesimals by the billions flying in every direction, some smashing into planets, others flung into interstellar space, still others settling into distant orbits where they remain today. This violence over in a few million years, but its consequences shaping the solar system, we observe 4.5 billion years later. After more than 3 decades since Voyager 2's brief encounters, the ice giants remain the least explored planets in our solar system. Every other planet has received multiple missions. Mars hosts a fleet of orbiters and rovers. Jupiter and Saturn have had dedicated orbital missions that studied them for years. Even Mercury has been visited twice, but Uranus and Neptune await their second visitor, and the scientific community has grown increasingly vocal about the need to return. Multiple mission concepts have been proposed over the years, each with its own priorities and technical challenges, all confronting the harsh reality that reaching the ice giants requires enormous patience and resources. Yet the scientific case for returning has never been stronger, and for the first time in decades, serious planning is underway to make these missions reality. The challenges of reaching Uranus and Neptune are substantial. At Uranus's distance of about 19 astronomical units from the Sun, a spacecraft travelling on a direct trajectory would require roughly 12 to 15 years to arrive. Neptune, at 30 astronomical units, would require 20 years or more on a direct path. These long flight times strain mission planning. Instruments designed in the 2020s would need to still function perfectly in the 2040s or 2050s when they reach their targets. Spacecraft systems would need to survive years in the radiation environment of interplanetary space. The mission team would need continuity across decades, with junior scientists becoming senior researchers during the cruise phase. One way to reduce flight time involves gravity assists from other planets, particularly Jupiter. By flying past Jupiter and using its immense gravity to change trajectory and gain velocity, a spacecraft can shave years off the journey. Voyager 2 used this technique, reaching Uranus in just 9 years and Neptune in 12 years from launch. However, gravity assists require launching during specific windows when planetary alignments are favourable, windows that might occur only every few years or decades. The trajectory that Voyager 2 used, visiting Jupiter, Saturn, Uranus and Neptune in sequence, won't be possible again until the 2150s. More limited alignments, allowing Jupiter assists to reach Uranus or Neptune, occur more frequently, but still constrain launch timing. The decision between a flyby mission like Voyager 2 and an orbital mission fundamentally shapes mission design and science return. A flyby offers relative simplicity. The spacecraft doesn't need to carry fuel for orbit insertion, reducing mass and cost, but provides only a brief snapshot of the system. An orbiter is much more complex and expensive, requiring a large propulsion system to slow down enough to be captured into orbit around the target planet, but it enables long-term study that transforms our understanding. The difference is the contrast between Voyager 1's Saturn flyby and Cassini's 13-year orbital mission. Both valuable, but Cassini's sustained observations revealed dynamics, seasonal changes, and detailed moon properties that no flyby could capture. For Uranus, the most mature mission concept is the Uranus orbiter and probe, which has received strong endorsement from the planetary science community. This mission would include an orbiter carrying a comprehensive suite of instruments: cameras, spectrometers, magnetometers, plasma and particle detectors, capable of studying the planet's atmosphere, interior, rings and moons over multiple years. Crucially, it would also include an atmospheric probe that would separate from the orbiter before orbit insertion and plunge into Uranus's atmosphere, measuring composition, temperature, pressure, and cloud properties as it descends. The probe would only survive for an hour or so before being crushed by pressure and incinerated by heat, but during that time, it would return the first direct measurements of Uranus's atmospheric composition at depths Voyager 2 couldn't observe. Such a mission would address fundamental questions. What is Uranus's deep atmospheric composition? And what does it tell us about where and how the planet formed? What's the source of the planet's heat budget? Why does it emit so little internal heat compared to Neptune? What's the precise structure of the magnetic field, and how does it vary over time? How do the rings and moons interact? What are the surface compositions of the major moons, and do any have subsurface oceans? How does Uranus's tilted configuration affect its magnetosphere, atmosphere, and moon system over its 84-year orbital period? An orbiter studying the system for multiple years, watching seasonal transitions and monitoring long-term changes, could answer these questions definitively. For Neptune, mission concepts have ranged from flybys focused on Triton to full orbital missions studying the entire system. Triton remains one of the highest priority targets in planetary science due to its active geology, thin atmosphere, potential subsurface ocean, and unusual captured origin. A Triton-focused mission might include a lander capable of studying the surface composition directly, sampling the organic compounds that darken Triton's polar ice, and perhaps even detecting seismic activity that would reveal interior structure. However, landing on Triton presents enormous challenges. The Moon's thin nitrogen atmosphere provides minimal braking for descent, requiring most speed reduction through rocket propulsion, and the surface temperature of -235 degrees Celsius creates challenges for power systems and mechanical components. An alternative Neptune mission concept would focus on the planet itself, studying its atmospheric superrotation, how winds blow faster than the planet's rotation would suggest possible, and monitoring the formation and evolution of those dramatic storm systems like the Great Dark Spot. Long-term observations would reveal whether Neptune has a seasonal cycle in atmospheric activity, whether storm systems follow regular patterns, and how the planet's internal heat drives weather despite receiving so little solar energy. Mapping the magnetic field over multiple rotations and locations would constrain interior models and help us understand how shell dynamos operate. The ideal mission would be a New Frontiers or flagship-class mission with sufficient budget and capabilities to comprehensively study either Uranus or Neptune over multiple years. However, cost realities make such missions difficult to approve and execute. A Uranus orbiter and probe would likely cost several $billion and require international collaboration to be affordable. Alternative approaches include smaller, more focused missions, perhaps a Discovery-class flyby mission that trades comprehensive study for faster development and lower cost, or a focused Triton orbiter that studies Neptune's most interesting moon in detail while observing Neptune from a distance. Recent technological developments offer new capabilities that Voyager 2 lacked. Modern cameras and spectrometers are far more sensitive, capable of imaging faint targets and detecting subtle spectral features. Radar instruments could penetrate beneath icy moon surfaces to detect subsurface oceans directly. Magnetometers with higher precision could map field structures in detail. Advanced systems, including radioisotope generators, more efficient than Voyager's, and possibly even nuclear fission reactors for high-power applications, could enable instrumentation impossible with 1970s technology. The scientific return from an ice giant mission extends beyond just understanding Uranus or Neptune. These planets serve as laboratories for studying processes relevant throughout planetary science: atmospheric dynamics under extreme conditions, magnetic field generation in unusual configurations, moon-planet tidal interactions, ring dynamics and stability, captured satellite evolution, cratered surface dating in the outer solar system. Every measurement we make at the ice giants informs our understanding of analogous processes elsewhere. Moreover, as we discover and characterize ice giant-sized exoplanets around other stars, our ability to interpret those observations depends crucially on understanding our local examples. When we measure an exoplanet's radius and mass, we use models calibrated against Uranus and Neptune to infer its composition. When we detect atmospheric features in exoplanet spectra, we interpret them using knowledge of ice giant atmospheric chemistry. When we try to predict whether a sub-Neptune exoplanet might have habitable moons, we draw on lessons from Triton and the Uranian satellites. Improving our understanding of Uranus and Neptune directly improves our ability to characterize thousands of similar worlds across the galaxy. The timing for returning to the ice giants has never been better. The planetary science community has reached consensus that ice giant exploration should be a priority. Technology has advanced to the point where missions once considered barely possible are now feasible. International partners including European, Japanese, and potentially Chinese space agencies have expressed interest in collaboration. Launch windows using Jupiter gravity assists are available in the late 2020s and early 2030s for Uranus missions, and throughout the 2030s for Neptune missions. The primary obstacles are budgetary and political rather than technical. These missions are possible if we commit the resources to make them happen. As funding decisions are made and missions are approved, developed, and launched over the coming years, we stand on the threshold of a new era in ice giant exploration. The generation that saw Voyager 2's groundbreaking flybys is passing the torch to a new generation that will see orbiters and probes return comprehensive data from these distant worlds. Students today who are inspired by the mysteries of Uranus and Neptune might become the scientists analysing data from these missions in the 2040s and beyond, finally answering questions that have persisted for decades and undoubtedly discovering new mysteries that we can't yet imagine. The patient giants await our return, orbiting in the darkness as they have for billions of years, their winds howling, their moons circling, their magnetic fields carving invisible structures in the sparse solar wind. They've waited more than 30 years since Voyager 2 passed through. They can wait a few more decades until we return with instruments and dedication sufficient to truly understand them. And when we do return, when orbiters settle into years-long missions studying these systems in detail, when probes plunge into those blue atmospheres and landers touch down on distant moons, we'll finally begin to see Uranus and Neptune not as distant curiosities glimpsed briefly in passing, but as the complex, fascinating worlds they truly are, ice giants hiding secrets we're only just beginning to discover. Welcome back here at the close of our journey through the distant realms, where Uranus and Neptune orbit in the blue darkness at the edge of our planetary family. We've travelled far tonight, exploring worlds that exist in twilight, where sunlight arrives as barely more than a bright star, where temperatures plunge to levels that solidify gases we think of as permanent, where exotic states of matter form under pressures we can barely imagine and barely reproduce in our laboratories. These ice giants, strange in their orientations, mysterious in their heat budgets, violent in their winds despite their distance and cold, represent frontiers of understanding, places where our knowledge remains incomplete, but our curiosity burns bright. Think about what we've discovered together tonight. We've seen how Uranus lies on its side, knocked over by some ancient collision, or gradually tilted through gravitational resonances, creating seasons that last decades and atmospheric patterns unlike anything else in the solar system. We've contemplated Neptune's impossible winds, roaring at speeds no planet should achieve, given the minuscule solar energy reaching that distance, powered by internal heat through mechanisms we're still working to understand. We've descended into exotic interiors, where water exists as superionic ice, where diamonds might rain through layers of conducting fluid, where magnetic fields are generated in thin shells rather than deep cores, creating twisted geometries that tumble as the planets spin. We've visited the moons, Miranda with its broken face, displaying geological violence far beyond what its small size should allow. Triton with its nitrogen geysers erupting in the coldest environment we've ever seen. Active geology, this captured world spiraling slowly inward toward its eventual destruction. Titania and Oberon and Ariel and Umbriel, each with its own story written in craters and faults and mysterious dark deposits. And all the small irregular satellites, captured fragments from the solar system's youth, still orbiting in their distant paths billions of years after they were trapped by ice giant gravity. We've examined the faint rings, those dark narrow bands shepherded by tiny moons, defying the tendency to spread and dissipate through gravitational choreography. We've celebrated Voyager 2's extraordinary achievements, that single spacecraft's brief encounters, providing literally everything we know about these systems up close. And we've looked forward to returning, to finally sending orbiters and probes that can study these worlds properly, answering questions that have lingered for decades and discovering new mysteries we haven't yet imagined. But perhaps most importantly, we've learned that Uranus and Neptune matter far beyond their individual properties. There are only detailed examples of the most common type of planet in the galaxy, Around other stars, in planetary systems scattered across the Milky Way, billions of ice giant-sized worlds orbit, most of them much closer to their stars than our ice giants, heated to temperatures where their ices become supercritical fluids or plasmas, but still fundamentally similar in structure and composition. Everything we learn about Uranus and Neptune informs our understanding of those distant worlds. Every model we develop to explain ice giant interiors, every insight into their atmospheric dynamics, every constraint on their formation and migration history helps us interpret observations of sub-Neptunes and mini-Neptunes around other stars. These distant blue worlds also remind us of deep truths about exploration and understanding. Knowledge comes slowly when the objects of our curiosity lie billions of kilometers away, when light takes hours to travel between us and them, when spacecraft require decades to reach them and can only visit briefly before continuing into interstellar space. Patience is required, patience to wait for launch windows, patience during multi-year cruise phases, patience as data trickles back across the vast distances, patience as multiple generations of scientists build understanding incrementally, each building on predecessors' work. Yet that patience is rewarded with understanding that transforms our place in the universe. When William Herschel noticed an unusual disk in his telescope in 1781, humanity's known solar system suddenly doubled in extent. When Adams and Leverrier used mathematics to predict Neptune's existence, and Galilei found it exactly where predicted, we learned that human understanding of physical laws had progressed to the point where we could find invisible worlds through pure calculation. When Voyager 2 revealed active geology on Triton and impossible winds on Neptune, we learned that the outer solar system remained capable of surprising us no matter how well we thought we understood planetary science. As you drift towards sleep now, your mind growing quiet, your breathing slowing, imagine looking back at the solar system from a great distance, from a vantage point beyond the planets where you can see the entire family together. The sun blazes at the center, the inner rocky planets hugging close to its warmth. Jupiter and Saturn orbit in their middle distance, massive and magnificent. And farther out, in the blue, darkness at the edge of the planetary realm, two smaller worlds circle patiently, Uranus rolling on its side, Neptune churning with its impossible winds, both surrounded by their retinues of moons and faint rings, both hiding their internal secrets, both waiting for us to return and finally understand them properly. These ice giants exist whether we study them or not, their atmospheres roiling, their interiors conducting heat through exotic physics, their magnetic fields carving space around them, their moons faithfully orbiting. They were there long before humans existed, will continue long after we're gone. Yet right now, in this brief moment of cosmic time, when our species has developed the technology to visit distant worlds and the curiosity to want to understand them, we have the opportunity and the responsibility to learn what we can, to satisfy our wonder about what lies at the edge of our cosmic neighborhood, to add these world stories to the great tapestry of knowledge we're slowly assembling about the universe. Sleep peacefully now, knowing that Uranus and Neptune orbit in their patient paths, that scientists around the world continue working to plan missions that will return to them, that future generations will study data from those missions and make discoveries we can't yet anticipate. The ice giants aren't going anywhere. They'll wait for us as they've waited for billions of years, as they'll wait for billions more, spinning in the darkness, keeping their secrets, beautiful and mysterious, and exactly where we can find them when we're ready to look. Dream deeply of distant blue worlds, of exotic physics operating in their invisible interiors, of moons and rings and magnetic fields and weather patterns operating on timescales beyond human experience. Dream of what we'll discover when we return, of the questions we'll answer and the new mysteries we'll uncover. And remember that the universe is full of wonders waiting to be understood, that every planet has its story, that even the distant ice giants, hiding in the outer darkness, have lessons to teach us about how worlds form and evolve and persist across the vast spans of cosmic time. Thank you for joining us here on Whispering Universes for this exploration of the ice giants, Uranus and Neptune, worlds at the threshold, hiding secrets we're only just discovering. Until we meet again under different stars, sleep peacefully, dream deeply, and remember gently that the cosmos holds more wonders than we can imagine, and that patient exploration slowly reveals them, one distant world at a time.